Thank you very much for introducing me and for the organizers for organizing this conference. I'm really happy to be here and to be in the ventilated room in this time of the day. So I will talk about this new framework that I proposed with Bertozzini and with Victor about cyclic quantum causal modeling. So we have heard about causal modeling this morning, but let me just set the scene so that we understand the notation that I'm using. So what we do in causal modeling is that we take some scenarios, like, for example, the Bell scenario that we have on this side, and we want to give to it a causal modeling. Like, we want to represent all the causal relations. And the way we do it is by using some directed graph, like the one on this side, where a directed edge represents some causal relation, and the nodes represent systems in our lab. Like, for example, here we have squares that represent some classical random variables, such as the x and y that each party produces based on the classical settings A and B, and then some circle nodes, which are some unobserved, either quantum or classical variable. So I hope all of you recognize that we have on one side a Bell scenario and on the other side what we would call the causal model of the Bell scenario. And in causal modeling, what we would like to have is, first of all, a valid probability rule that allows us to evaluate the probability over observed variables once we have the causal mechanisms, and then some other tools that relate this probability rule to the graph properties. And these are called graph separation theorems. And in our work, we focused on the cyclic version of causal modeling. So we allow our circuits, like the one on this side, to be cyclic. Like in this case, we have the output of one node that is fed back as an input of the other one, and vice versa. The same happens on the other side. And when we do causal modeling, the difference that we would have is that we would represent this with a cyclic model. But the idea is the same. So also in this case, we would like to have a valid probability rule, which allows us to evaluate the probability over x, y, a, and b, given the causal mechanisms, and some other result that links the probability rule to the graph properties. So why do we care about cyclic models? The motivations are, like, they appear in many different fields. So on one side, we have some solutions in general relativity which are closed in space-time. So in principle, if we had a quantum process happening on these curves, this would be described with a cyclic quantum causal model. Then indefinite causality can also be described with causal models, cyclic causal models. So here we have, for example, a superposition of causal orders. So in one case, one agent acts before the other one, and in the other case, the second agent acts before the first. And if we take a superposition of this, we can describe it using cyclic causal model. And finally, in the purely classical case, well, not finally, we have many other reasons, but in the purely classical case, if we have feedback processes, so where, for instance, like in the double pendulum, we have the two angles that depend on each other in a feedback way, we can also describe this with cyclic models. So many reasons, even more than the ones that I'm studying. But even when we try to do the first step of defining a probability rule, we run into problems. So in this case, the idea is that you're given a graph, like for instance this one, and you put on top of it some causal mechanisms. So this would be CPTP maps for the unobserved nodes, and some POVMs for the observed nodes, which tell us how to get the classical variable. We would like to have a joint probability distribution over the x and y, so the outcomes of these measurements. And we know that if the model is acyclic, there is a valid probability rule, which is simply the known Born rule that we always use in quantum mechanics. But if the model is cyclic, there is no valid probability rule which holds for arbitrary causal models on arbitrary cyclic graphs. What is known is just a probability rule for a strict subset of causal models, which satisfy some strong consistency conditions. And what we propose with this work is a probability rule which works for any causal model on arbitrary graphs, so for causal models that are finite dimensional. So we want to have finite dimensional Hilbert spaces and finite cardinality random variables. So I will just give you an idea of how we construct the probability rule. This talk is more meant as an invitation to read the paper or to talk to me or Vilazini in the next few days. But the idea is that we take the cyclic graph for which we want to define the probability rule, and we construct a mapping from the cyclic graph to an acyclic one. Once we have this mapping, we can then use the known probability rule for acyclic causal models and try to construct our rule. And now this mapping uses a tool which is the so-called post-selected teleportation protocol. So the goal here is to take loops and remove this cyclicity and trade it with some acyclicity. So what we want to do is to take directed edges, which are identity channels, and simulate them with other nodes and edges. So now, I hope we all know the teleportation protocol. So this is a protocol that allows you to simulate an identity channel by having some shared entanglement here, performing a Bell measurement here, and then applying a unitary correction depending on the outcome of the Bell measurement. And the interesting part of this is that if we focus on one specific outcome of this measurement, namely the psi00 outcome, then there is no correction to be applied. So the correction that we would apply here to simulate the identity channel would be just the identity. So our idea is to simulate this directed edge, so simulate the identity channel, by using the post-selected version of the teleportation protocol. So we have this set of nodes and edges where we prepare a Bell state, we post-select on the specific outcome that does not require any correction, and this all together allows us to just take an edge and replace it. So using this, what we can do is to, as I was saying before, take any cyclic graph, apply this reduction procedure on the loops, and obtain an acyclic graph like this one. And once we have the acyclic graph, we can look at the probability distribution over the variables we care about, so x and y, and the Bell measurement that we have introduced. And if the probability relative to the outcome that we care about is non-zero, then we can take the conditional probability on this outcome. Okay. So this construction allows us to define the probability rule in arbitrary cyclic causal models by just using this mapping that we have. So this is one step, and now the second step that we would like to have in causal modeling is to relate this probability rule to properties of the graph. And this is what we call what are called graph separation theorems. So for example, the idea is that if you're given a graph and a probability rule that is compatible with the graph, on one side you can define properties of the graph only. So for instance, there is this d-separation property, which I'm not defining here, but I just want to give you the idea, which is simply a property of the graph. And for instance, in this example, so here we have three simple nodes, we would say that A is d-separated from B, and A is deconnected from B condition on C. Again, I don't want to define this property, but the idea is that if you look at A and B, there is no direct connection between the two, because all the edges go through C. And for this reason, well, looking at the definition, one would end up saying that A and B are d-separated and deconnected once you condition on C. But on the other side, if this is a property of the graph only, you can have properties of the probability rule. So you can look at all the causal mechanisms and the probability that you have defined, and look at independencies in this probability rule. Like, for example, as we would all say, like if A and B are independent condition on C, if the probability rule factorizes in this way. And the graph separation theorem does connects these two facts. So on one side, properties of the graph only, and on the other side, properties of the probability rule that one can construct from the causal mechanisms of the graph. And this is particularly strong because if you just have the causal model, but you do not have the causal mechanisms, you can still infer what independencies will hold in the probability rule, even without the causal mechanisms. In more details, the d-separation theorem is twofold. So this holds for acyclic graphs, so arbitrary causal models on acyclic graphs. And on one side, we have one property, which is soundness. And this tells us that every time we have deseparation at the level of the graph, the same independency will hold at the level of the probability distribution. Meaning, as I was saying, that it doesn't matter which causal mechanism we have on the graph, on the causal model, the probability rule would factorize in a very specific way. And on the other side, we have completeness, which tells us that if we have deconnection, so if the variables are not deseparated in the graph, then we can construct at least one causal model where the variables are correlated. But sadly, this property fails when we look at arbitrary cyclic graphs. So if we have causal model on a cyclic graph, this will not hold. And our idea is to define a new graph separation property, which we call p-separation. As a graph separation property, this is only something that you can get from the graph without needing any information on the causal mechanisms. And I will not give the definition, but the idea is that once you have the graph and you want to define this p-separation, you would look at the image causal model. So you would do the same mapping from cyclic to a cyclic with post-selection, and look at deseparation conditioning on these post-selection nodes. So the definition is quite involved in here, but the idea is that you can relate p-separation to deseparation with extra conditioning. And using this definition, we're able to prove the same theorem. So we're able to prove that for any graph, on one side we have that p-separation implies conditional independency in the probability rule that we have constructed. And we're able to prove completeness. So if we have p-connection, then there exists at least one causal model where the variable become correlated. And this holds for arbitrary causal models as long as they're finite dimensional. So we have finite dimensional Hilbert spaces and finite cardinality random variables. So with this, I will just flash some further results with the idea of if you find anything that would interest you, you can just come to me and talk to me or just read the paper, or to Vilasini. So on one side, we have one paper that is fully focused on the classical results. So we have some further results that just hold in that case. Then we have one full chapter where we link all causal modeling frameworks that are known to us and characterize what are the inclusions and properties between those. We have a whole study on post-selected teleportation protocols, because in this talk I presented this Bell teleportation protocol where we have Bell state and a post-selection on a Bell state, but actually there is a whole class of protocols which have the same property and allow us to define the same probability rule. And then we have two works, one on interventions and one on connecting tensor networks to cyclic causal models, which are both in preparation and will be out sometime in the next year. And with this, I thank you, and I will flash some Outlook for the same purpose.
To just repeat the p-separation and how it avoids the problems that you will have if you apply d-separation to cyclic models.
Yes, so if you apply d-separation to cyclic models, you do not get the same properties. So you can construct models where you have d-separation but correlated variables. And the idea of p-separation is to have a completely new definition, which is based on having this extra conditioning on the post-selected nodes in the teleportation.
So it's d-separation in the post.
More or less.
Is p-separation like d-separation in the post-selected?
Not exactly, because when we do this mapping, you can have many causal models that that can be constructed in this way. So it's a condition on this whole class of causal models. But yeah, roughly yes, like you can define it as d-separation with the extra conditioning on a whole class of causal models.
So I have one very quick question. Could we simulate a Paiva sheet with this model?
Yes, that's this is like the grandfather paradox kind of, they're all described with cyclic causal models. Yeah.
Thank you very much. Let's take again, Pablo.
teoria sì.
Yes, please. Aspetta, che è saltato tutto. Aspetta, wait.
Ah no, qualche volta si fa nero, ma basta che
ok.
premi 2 volte
Ok,
e si
scusa.
risolve, non so
Perfetto.
perché.
Va bene. Sì, è stato messo dura troppo. Grazie. Ah già. Ah. Milano. Milano.
Quale vuoi fare? Questo come questo?
Beh, anche questo, sì. Va, 1, 2, ah sì, scusa. The other one? Yeah. Yeah, shall I start? Should I start? Thank you very much, and good afternoon, everybody. Thanks a lot to the organizers for giving me the opportunity of being here in this great and very interesting conference. So the main motivation behind this work is essentially of fundamental nature, and it's to understand the difference between the classical and the quantum description of the physical world. Essentially, where a big disclaimer, everything here will be non-relativistic. I will just mention at the end some possibility about the relativistic, how to extend to the relativistic scenario. So what we have in mind is what you can see here sketched in the figure. And essentially, the idea is that the scenario we consider is that we have a system and we measure it at subsequent times, where these subsequent times means essentially two things. First of all, that we take into account the evolution in between the measurements. So in between the measurements, the system evolves. Not only that, but we take into account that the system, like any actual physical system, will be interacting with something around it. So it will interact with its environment, and so it has to be treated as an open quantum system. And the idea, so the whole point is that we have these multi-time probabilities as input, and we want to understand whether they are classical or quantum. So whether they come from something like more like a gear, let's say, or more like an atom. And of course, I mean, the question of the difference between quantum and classical description of the physical world is as old as quantum mechanics. But as we know recently, it has attracted renewed interest, let me say, from a fundamental point of view, of course, but also from an applied point of view in many, many different research areas. You see here some representative examples. And essentially, this question is the central question whenever we have a certain phenomenon. We think it's quantum, but we want to ask, so to speak, seriously whether it's a quantum phenomenon or not. So if we want to ask seriously whether we can exclude the existence of any possible classical description of this phenomenon, right? Not only that, so that's one of the central questions of this talk. The other one is, let's admit that we can do that, we can exclude that something has a classical description. We want also to move one step further and to say what is the key property, the key quantum property that discriminates between quantum and classical. Is it quantum coherences? Is it quantum correlations? Does it depend? As we will see, it depends. So we deal with open quantum systems. In one word, this means that we consider a bipartite system, essentially, the open system that includes all the degrees of freedom we are interested in this setting, the degrees of freedom we are going to measure, and then the environment that contains everything else. We don't forget about this everything else because we want to know its impact on the open system, but we don't want to resolve this environment. So what we do is an average. We average out the environment, and this is done via the partial trace. If we move from closed to open systems, one thing to pay is that we can no longer use unitary evolutions to describe the evolution of the open system. But the good thing is that at least if the initial state of the system and the environment is initially a product state, so the two are uncorrelated and the initial state of the environment is fixed, then we can replace unitary dynamics with a well-defined and powerful mathematical tool that is given by completely positive and trace-preserving maps, so CPT maps. We have all the apparatus of CPT maps, Krauss decomposition, Choi representations, for those of you who are familiar with these notions. So once we have the dynamical maps that describe the evolution of the state of the open system, then we can extract the information about the probabilities of affecting any measurement, the measurement of any observable of the open system, let's say a projective measurement for the sake of simplicity, at any single time. So from this, we have single time probabilities. But as said, we want to look at multi-time probabilities. And how do we do it? So imagine that we have our open system, we measure it at a certain time t1, time t2, and so on. And we want the joint probability distribution of having outcome x1 at time t1, x2 at time t2, and so on and so forth. When we don't know what to do, so to speak, we have to go back to the axioms of quantum mechanics. We have to go back to the Bohr's rule. Essentially, if you want Bohr's rule plus the projection postulate applied iteratively. And then this probability is given by taking the initial state of the system plus the environment, applying the evolution of the two, and the global evolution is a unitary evolution. We assume that the system plus the environment is closed. We can always take an environment that is as large as needed for this to be the case. So we have initial state, unitary evolution up to the time of the first measurement, and then we apply the two projectors. Again, for simplicity, we will just speak about projective measurements at the left and the right associated with the first outcome, right? So this would give the post-measurement state after normalization if we had only one measurement, but we have many. So now we apply again the unitary evolution from T1 to T2, other couple of projection, and so on and so forth until the last interval. And this is the definition, if you want, of the multi-time probability distributions we will work with during the whole talk. The key point here to note is that even if these projectors are referred to the open system, so we are measuring only the open system, still to evaluate this quantity, we need to refer, at least initially, to the global unitary evolution. While here we can evaluate probability with an object that lives only at the level of the open system, here we have to go back to the global unitary evolution because it's a multi-time object. Okay, so this is the object we will deal with. Our central goal is to understand when this is something classical, when this is something non-classical, so we need a definition of classicality. And in this context, there is a natural, if not mandatory, if you want, notion of classicality, that is the validity of Kolmogorov consistency conditions. Kolmogorov consistency conditions are those that characterize classical stochastic processes and that essentially relates joint probabilities. So if we take joint probability distribution and we sum up over all the possible value at any time, possibly also at an intermediate time, we end up with a joint probability distribution at the lower level of the hierarchy. So we start from three-point joint probability distribution, we sum up over all the possible value at intermediate time, and we have the joint probability at initial and finite time. So joint probability distributions of classical stochastic processes satisfy these. Not only that, but crucially for us, also the converse statement is true. So imagine now that we are given, as said at the beginning, a collection of joint probability distributions that maybe they come from experiments, even directly, or also from the quantum modeling we are doing of something. And we verify that this joint probability distribution satisfy this Kolmogorov consistency condition, so this hierarchy of condition. Then, by virtue of the Kolmogorov extension theorem, we know that it exists a classical stochastic process with exactly the same joint probability distributions. So it exists, if you want, an alternative classical description of our phenomenon, of our statistics. Of course, the theorem is about the existence. I mean, this might be also, let's say, a rather ad hoc, peculiar process, but it exists. And then any claim about the quantumness of what we are dealing with will not really be justified, right? Because we would have an alternative classical description. So this is the criterion, strict criterion for classicality we were looking for. And let me mention also that this here notion of, I mean, there are hundreds of different and non-equivalent notions of classicality. Here, classicality is understood really as the possibility, at least in principle, to perform non-invasive measurements. So to access the true value of a physical quantity, without affecting the subsequent statistics. It's exactly the same notion of classicality that is at the basis of Leggett-Garg inequalities, for those of you who are familiar with that. And as we know, in quantum mechanics, measurements are invasive. So in quantum mechanics, in general, Kolmogorov consistency conditions will not hold, right? Because even a non-selective measurement, even if we perform a measurement and we sum up over all the possible values, so we forget about the outcome of the measurement, we are modifying the state of the system. So we are modifying what will come after, so to speak. And the reason for that is that essentially we are destroying the coherencies with respect to the measurement basis. So from here we already see a connection with the quantum coherencies, but to really, say, clarify it, we need one further ingredient in our discussion that precisely has to do with the Markovianity of the statistics, with the Markovianity of non-Markovianity of the statistics. Also here, I mean, the notion of Markovianity in the quantum regime has even more definitions, let's say, non-equivalent among each other. But here for us, Markovianity means the validity, essentially the validity of the quantum regression theorem. So loosely speaking, the quantum regression theorem tells us that if we can neglect the impact of the correlations built up by the interaction between the open system and the environment on the subsequent statistics, then we can write the multi-time probabilities that we defined before in this way here. And you might see, if you remember the formula we had before, we had something very similar. So state, projectors, propagators, and so on. But before, we had the global unitary evolution. While now, we have the propagators of the dynamics of the open system. This is a crucial point. So if the quantum regression theorem holds, also the multi-time probabilities can be written in terms of dynamical maps. So can be written in terms of objects that live on the set of states of the open system only. And this condition, under proper, let's say, assumption, if we consider non-degenerate observable, is precisely the counterpart of the condition of Markovianity, the, let's say, original definition. So Markovianity of classical stochastic processes. The definition that you see here, that essentially, let's say, Markovian processes are those where you can neglect memory effects. So if you have a conditional probability over a whole previous history, this will depend only on the last assumed value. Even more importantly, if the process is Markovian, then you can reconstruct the whole hierarchy of joint probabilities with this formula. So relying on the first level of the hierarchy and the one-to-one conditional probability. So you can build up the whole hierarchy only from the lowest levels. And from this, you see the analogy with regression, and we will need this later, I mean, in a second. If Markovianity holds, we can establish a connection with quantum coherence. So quantum coherence in the sense the off-diagonal elements of the state, in this case with respect to the measurement basis. It's not simply the presence of coherence. We need something a bit more refined. Without much fantasy, we call coherence generating and detection. And so, which is expressed by this inequality here. I mean, I don't go in details of this. This means essentially, as the name suggests, Coherence generating and detecting means that the dynamics is able not only to generate coherence, but also then to turn them into population at the later time of the dynamics. You have an exchange between coherences, population, so population, coherences, again populations. And what we have shown is that if we consider a sequential measurement of a non-degenerate observable of an open quantum system, if the statistics is Markovian, so if the quantum regression theorem holds, then for any initial diagonal state in the measurement basis, we have a classical statistics if and only if the dynamics is not CGD. So in other terms, if the statistics is Markovian, the non-classicality is in one-to-one correspondence between the capability of the dynamics to generate coherences and turn them into populations. And let me stress here that the non-trivial point of all of this is that we are relating a property of quantum coherence, of the dynamics of quantum coherence, so a property that lives at the level of dynamics of one time, with the property of the whole hierarchy. And in general, of course, we can go from up to bottom via marginalization. Even at the quantum level, we can simply marginalize over the last one, but we cannot go the other way around. As said, unless the statistics is Markovian, because if the statistics is Markovian, we reconstruct everything from the lowest order. And that's why Markovianity is key in order to establish a correspondence between classicality and something that lives at the level of the dynamics, so the dynamics of quantum coherence. I think I don't have time for the, how much is 1:30 seconds? Okay, just to mention, as we also then investigated the non-Markovian case, I will just, let's say, mention what is the key ingredient. We cannot rely on dynamical maps, but there is a more general tool we can use, and this is quantum comps. Quantum comps that we have already heard in this conference, and we will hear again during the next days. So this can be used also to apply to treat the non-Markovian case, where now the key property has no longer to do with something about the dynamics of the open system, but can be linked to something that has to do with the dynamics, the global dynamics, and in particular system-environment correlations, not in the sense of entanglement, but in the sense of discord. Discord was, let's say, is a notion of system-environment correlations that is stronger than entanglement, and one can have a one-to-one correspondence with discord in the general non-Markovian case. And so this is the conclusion. As just last remark, of course, you might wonder how this can be, let's say, extended to the relativistic regime, and hopefully this will be one of the outcomes, or at least we will start in that direction in the cost action, in particular in the working group 3. So stay connected for that. And thank you for your attention.
So at the very end, I think you were saying that so your definition of classicality essentially is definition of coherence, right? Of of incoherence.
It is Kolmogorov. The definition of classicality is Kolmogorov. Then if quantum regression theorem holds, so if the multi-time is Markovian, it's in one-to-one with coherence.
I see. And if it's not Markovian, you are still talking about coherence, right?
Then coherence plays essentially no role. So we have examples of dynamics of situations, so multi-time statistics that are non-classical, even if coherence is never generated. And
okay, so maybe if you can very quickly remind what is your definition of classicality for the non-Markovian case, very, very briefly.
It's still the, let's say, the definition, the original, so it's still the validity of the Kolmogorov consistency condition, that then in the non-Markovian case, using comps can be directly, let's say, turned into this, let's say, via this relation that relates comps via the Choyami-Olkowski isomorphism. This becomes the fact that essentially full dephasing map is non-invasive, is a non-invasive action for comps, so it's equivalent to the identity. This is, in the language of comps, would be our definition of classicality. It's a kind of multi-time coherence, if you want.
Let's thank.
No.
Okay, let's thank Mele again. the next speaker, you can sit here. And someone asked me about writing the names. The last sheet here, you can write your name if it's not already here. So feel free to come here and sign your name.
Pointer? How do I put this? Here. Good luck. Grazie. Oh yeah, this is going to work? Yeah. Yeah, there's one here. Oh, nice. And then just... Yeah.
Then, now we have Matteo Zambianco from the University of Waterloo with the twin paradox in quantum field theory.
Good afternoon, everyone. First of all, I would like to thank the organization for having me here today. So today, I would like to talk about the twin paradox in quantum field theory. This work in collaboration with Thales Rick Perch. What I prepared for today. So my mission today is to first convince you that particle detectors can be used to model clocks that take into account effects from quantum field theory. And then we're going to use those clocks to propose a twin paradox scenario. Oh, okay. And then we shall use those clocks to study what we can learn about time if we consider a twin paradox scenario with those clocks. So, right, so let's understand how can we use particle detectors as quantum clocks. So nowadays, the best clocks that we have available in the scientific market are the atomic clocks. When it comes to atomic clocks, the physical principle behind it is quite simple. They essentially use the oscillation between two quantum states of an atom to define a frequency of standard. And once you have a frequency standard, you have a periodic event. You can use that to naturally define measurements of time. As an example, the second is defined as the transitions between the hyperfine levels of the ground state of the cesium 133. Those oscillations between the states of the atom, they are driven by an interaction with the laser. So the physical description behind an atomic clock is an atom interacting with an electromagnetic field. Therefore, if we wish to consider the effects of quantum field theory in time, particle detector models provide a natural description for interactions localized in space-time that capture the essential features of the light-matter interaction. Now, let's pay a little toll here and quickly revise what do I mean by a particle detector. For this talk, I'll be using the Unruh DeWitt model, where we have a qubit, a two-level system that interacts with a quantum field. So this is my, my model. This is my interaction Hamiltonian density. The lambda function, the Smirne function, tells me how my interaction is going to be localized in space-time. Tau is the proper time associated to the center of mass of the detector in space-time. Mu can be any observable of my atom. We usually make this choice here, the monopole moment. And omega is the energy gap between the two levels of my atom. So here, I'm going to consider the following. I'm going to prepare my atom in the excited state, and my field in any state that has vanishing odd point functions. For instance, let's take the vacuum to make our life easier and happier. Now, a natural question that one can ask is, what's the probability that my detector might decay? What's the probability of my detector transitioning into the ground state? Using perturbation theory, we can answer this question. It's given by this beautiful expression here, where we have terms that are, we have the smearing function telling essentially the shape of my interaction in space-time, and all the information about the field is encoded in the Whiteman function. Now, how can we use a particle detector to build a quantum clock? Before proposing our model, I would like to propose two motivations. First motivation, the Urudowit model captures the essential features of the light-matter interaction in the absence of angular momentum. So, and how is that? Let's consider a simple model where I have an atom, ground excited states, fixed energy gap, and my atom is interacting with the electromagnetic field. So I have my dipole here. So now, if I were to write the wave functions for my ground and excited states, and then I write my dipole operator in terms of the basis states for my atom, it turns out that the smearing function naturally appears here as being encoding the information about the spatial localization of my atom. So the analogy that we establish here is the following. Because my field here, the scalar field that I was considering before, is just the scalar version of this, and the monopole moment is also a scalar version of the dipole operator. Now, second motivation, let's consider a point-like detector in space-time. I'll have my switching function controlling how long my interaction with the field is going to last. So it lasts for a certain time, say t, and my detector is point-like. It turns out that if I compute the probability of my detector decaying, in this case, what do I get if I divide by the total time of interaction is something that's proportional to the energy gap. So therefore, I can use this system to define a clock with a given frequency omega. So given those two motivations, our model for the clock is we're going to use the average decay rate of my atom to define the measurements of time of our clock. And how this is going to work, here I have my atom doing space-time things. I have two events that they pertain to the center of mass of my detector, and then the time associated between those two events is going to be simple inversely proportional to the average decay rate, where kappa here is just a constant that defines my scale for time. It's important, I would like to call attention here that this is a clock that takes into account quantum field theory, because even though I'm using a qubit interacting with a quantum field, considering particle detectors is equivalent to considering localized quantum fields, as shown in this work here. So with this, we came to the end of the first part. Now that we proposed the model for a clock, I'm going to consider a twin paradox scenario with this model of clock. But first, let's review what do I mean by the twin paradox. So the standard scenario, we have Alice and Bob, and they have the same age. Trust me, they don't look like, but they are twins. Alice is just chilling. She's here in Naples, sweating. And then Bob goes on a round trip to Canada so he can feel a little bit cold, and he comes back. By the time he comes back, Alice is older than Bob. The paradox, quote unquote, comes from people the first time they're told this, they say, wait a minute, I think the situation is symmetric because you can think that Bob is just steady, he's just staying on Earth, and then Alice is traveling. But this is not true, and you can see by, if you analyze the rest surfaces of Bob, they're not continuous, and therefore the situation is not symmetric. If you consider any time-like trajectory, an accelerated one for instance, the situation is even clearer because the twin that's going to measure the longest proper time between two fixed events is going to always be the one that stays on Earth. All right, so now, and also by considering an accelerated trajectory, we don't suffer from the ill-definedness of the planes of simultaneity. Now, if I consider accelerated trajectories, Bob's rest surfaces, they are indeed continuous. Okay, so now what I'm going to consider, Alice is going to stay on Earth, and Bob is going to follow an accelerated trajectory such that both my twins start and end at rest. Because I would like to be able to compare my two clocks, so therefore I'm enforcing that they start and begin their motion, start and end their motion at rest. Between A and B, Bob is going to measure. Suppose Bob also has a classical clock. This classical clock is going to associate a proper time t, and this is going to be the proper time for Alice, where A is the proper acceleration associated to the portions of the trajectories. Now, my twins, on top of carrying a classical clock, they're also going to carry my quantum clock. They just bought it today, fresh from the market. And Alice is going to follow this trajectory. Bob's going to follow this one. And what I'm going to consider here, my space-time mirroring is going to be such that the spatial profile of my detectors is described by a Gaussian. So I have a finite size atom, not a point-like one. And the switching is just turn on off between here and here. Now, what we did, using this model, we computed the decay rate for Bob and for Alice. And here we have the numerical result. Remember that we are measuring time using the transition rate, the average decay rate. So if I wanted to analyze the ratio of the time measured by Alice and the time measured by Bob, according to our quantum clock, what we see is quite interesting because we have a region here where the twin that stays on Earth actually measures less time than the twin that travels. And this is quite interesting because this is a total new effect. So quantum field theory is telling something about time to us here. At the same time, if I consider the limit of long interaction times, I do recover the prediction from special relativity, meaning that the ratio between the time measured by Alice and the time measured by Bob is simply the ratio of their respective classical proper times. Now you might think, wait a minute, this might be just numerics, and I don't trust numerics. But we do have a theorem to justify this behavior in the long interaction, in the regime of long interaction times. So it turns out that, I'm not going to delve into details here, but if we consider arbitrary trajectories in Minkowski space-time, and if we consider the expressions for the decay probability, it can be shown that in the limit of a point light detector that interacts with my field for long enough, the ratio of those decay probabilities, they indeed approach 1. And therefore, we recover the classical prediction. We recover what special relativity teaches us about the twin paradox. All right, so what's the take home here? So first, I show that particle detectors can be used to construct clocks that consider effects from quantum field theory. So the clock that we're proposing here is fully featured in quantum field theory. Now, in a twin paradox scenario with particle detector-based clocks, we identify a regime corresponding to short interaction times with the field where the game changes, where the twin that stays on Earth can actually measure less time than the twin that travels. But also, in the classical regime, where my clock interacts long enough with the field, we see that our results make sense because we recover the prediction by special relativity. A question that I would like to leave it open here is, what does our model teach us about the causal structure of space-time? Because in the short interaction regime, we're actually changing the order compared to what we see in special relativity, in the sense that, quote-unquote, the twin that stays on Earth is younger than the twin that travels. All right, and this work is to appear in archive soon. And yeah, thank you so much for your attention today.
Just one quick question. So the next speaker can already come and set your.
Thank you. I was just wondering if you're working with particle detector as your clock, but if you're accelerating it to a twin paradox scenario, do you expect there to be some sort of influence from effects like the Unruh effect or like Unruh radiation on your clocks? Would that
Sorry, can you speak louder? I
lost
you in your
the mics aren't working. I just want to know do you expect there to be some influence from effects like the Unruh effect or Unruh radiation when you're dealing with accelerated detectors when you're using them as your clocks?
Exactly, we do. But the point is that my claim is that we should consider if we want to use this to model a clock, and if this clock makes sense, as I claim that it makes, then this is telling something about the nature of time in the regimes where I interact with my field in very short time scales. Okay. But yeah, I agree with you.
Thank you.
Right. Oh yeah, sure.
Thank you very much. So, you are Marius Krumm from Innsbruck. Can you put this on your shirt? It's the microphone. This is the microphone for the Zoom.
Yes.
This is for the audience and this is for the Zoom. Our next speaker is Marius Krumm from the University of Innsbruck with what process matters tell us about the quantum space. I will tell you when it's 5 minutes, okay?
Okay, thanks a lot. Yes, so until a few years ago, I've been working a lot on process matrices, which are a particular approach to operational phenomenological aspects expected in quantum gravity. But in the recent years, my impression was that the field has mostly died down, which is a pity because there's a lot of unrealized potential. So in the first half of the talk, my goal will be to just show one example for how to combine process matrices with approaches towards quantum spacetime. And in the second half, I want to give some new impulse, some new ideas for how to continue working with process matrices. So process matrices were already mentioned qualitatively by Emily Adlam. And the basic idea is to go to the classical notion of causal structure first, which is about cause-effect relations, and which we have seen in the first presentation in this session. But in quantum gravity, where we have both a dynamical light cone structure and potentially or hopefully a quantum light cone structure, the cause-effect distinction starts to become blurry. Like the easiest example would be that quantum uncertainties blur light cones. And to get more of an operational grip of what's going on, one goes back to Einstein elevators, in which physics is assumed to be, how should I say, very textbook. And one imagines there being an agent in the elevator, and at some point it receives a quantum system from a lab, which might be its own quantum probe that the agent sent out. Then the agent can apply an arbitrary quantum instrument to that probe, records the result. The quantum system goes out again. And one very important thing to mention here is that instead of just passive observers, like usually in relativity, there are active agents who can actually act with a chosen quantum instrument. And the typical example for something like that would be the quantum switch, where a qubit decides whether an agent A sends a quantum signal to B, or B sends a quantum signal to A instead. To mathematically describe process matrices, one uses a very helpful yet simple tool, which is called the Choi-Jamiolkowski isomorphism. And it can turn quantum channels or quantum instruments into operators, and which actually has a nice interpretation. So one considers a maximally entangled state, sends it through the quantum channel, so sends one half through the quantum channel, and there you go. Now you have a density matrix, and it carries all the information about the quantum channel in it. And since it's now a density matrix, what was before a quantum channel, this allows us to adapt a lot of the mathematical tools that we are used to from textbook quantum mechanics. And one of these tools is a generalized Born rule, where the density matrix is now replaced with the process matrix, and the POVM elements are replaced with the agent's instruments in the Choi picture. And the only requirement is that one just essentially wants valid probabilities. But this has also harmed the field because we simply don't know which processes are physical, and we don't have many axioms to actually decide this. But one postulate that does exist is that one demands a certain kind of purifiability or dilatability. So as shown in the lower picture here, one dilates the quantum instruments of the agents by explicitly modeling a quantum memory that has a zero or an identity time evolution when it's free. And one also introduces a global future up here and a global past up here. And then one demands that one can replace the process matrix W with a unitary G that is allowed to depend on all the agent operations. That always has to be unitary. So to present one former project where one brings in approaches to quantum space-time together with process matrices, I'm presenting here an old project on the Page-Wouters formalism. So the idea here is to model the time perception of an agent that's undergoing a quantum causal structure. And for that, one assumes that each agent has their own quantum clock that is measuring essentially their proper time. And then one writes down so-called history states that also model time. So the first term here is what you would consider a usual Schrödinger type quantum state. But we have additional Hilbert spaces for the quantum clocks now. And we are assuming here that the time eigenstates are orthonormal to each other. And one important thing that we are doing differently here is that we are actually assuming that the quantum clocks are discrete. Then in the continuous case, one would define an agent's perspective by just projecting on the time of that agent. But it turns out that because of the discrete clocks, just having that doesn't allow to really model any interesting indefinite causal structure. So we dealt with that by introducing normalization operators, which I'm kind of thinking of as a density of times, because time dilation can make one time step longer or shorter, at least as perceived by other agents. And we are compensating for that by the normalization operators. So together with the history states that are shown here and the definition of the perspective of an agent, one more ingredient that we are putting in is that an agent sees the usual unitary time evolution happening to the other systems, because usually agents don't describe themselves and they still see lots of unitary time evolution. And there is one time that is special, which is the time of action, where within its laboratory, the agent forces a particular unitary operation, its own unitary operation, while the outside does whatever. The agent doesn't really care at this point. So if we take everything together, what we get is something that would be called the causal reference frame, where the time evolution and agencies decomposes into a unitary of the causal past, its own action, and the causal future. And then the full time evolution from beginning to end is actually given by a purified process matrix. So now we finally have the purified process matrix. And it turns out that our requirements are actually quite restrictive. So the time evolution that an agent sees from the beginning to an arbitrary time has to be essentially affine linear in the operations of the other agents. And in the original paper on causal reference frames, this was not a result that applied to them. So for the so-called reversed Lugano process for an agent A, they had a causal reference frame that looks like this, whereas so here you see the time of action of the agent, but in the causal past you're having operations that are obviously not affine linear in the operations of the other agents. So this would not apply in any way to our new setup that models time. So, as promised, I will now talk about new directions for process matrices. And I have begun to work on this with David Trio from CUNEF University in Madrid. And one thing that he noticed is that process matrices always assume fixed dimensions. They don't allow you to vary the dimensions of any of the probes or whatever. And if you think about any real physical situation, for example, quantum gravity, like it should still have something to say if you change the dimensions of some quantum probes, like something should still happen. And one might make it a design principle or even a postulate that the generalization of the process matrix or the restriction of the process matrix should make statements about probes of any dimension. But we had severe problems actually phrasing a satisfying postulate for that case. So I tried to come up with something more specific that is still a form of generalizability postulate. So another thing that one might notice in process matrices is that the number of agents is fixed. And also that is strange in a real physical situation, because one might consider just introducing a different agent, for example, an agent that secretly captures a probe of another agent, does an operation on it and sends it out again. So a physical situation does something to such changes, but this is not reflected in the process matrix framework so far. So something that one could do is one takes the causal reference frames that model the perspectives of agents, and one demands that for any of the systems of the, or should I say, finite-sized quantum systems taking part in this, that one can just introduce another agent, in this case D, shown here in purple, that can apply an arbitrary dilated unitary. And then one demands that even with this change, if it's the true causal reference frame of the agent, like a valid real description of what's going on outside, then this should also give a valid process matrix. And mathematically, I expect this to be highly restrictive because these causal reference frames are usually highly fine-tuned and highly fragile. The very last thing that I don't want to mention is on a more practical side, because I think a lot about how to bring quantum machine learning into relativistic quantum information. And maybe one of these things is sort of obvious for somebody with a background in quantum machine learning. So very often, just like with non-locality and Bell inequalities, you also have causal inequalities, and you are wondering what is the strongest violation that you can get with your model. So with a machine learning approach, you would take this causal inequality and phrase it as a so-called loss function that you want to minimize, which in this case is essentially just a multiplication with a minus sign. And then you use a parameterized ansatz for the unitaries and the process matrix, which is given by a layered structures of parameterized Euler rotations and fixed entangling gates in the so-called hardware-efficient ansatz. And then you just optimize this with gradient descent-based methods and see what you find. So, yes, so I've given you two new directions, one of them foundational, introducing extra agents, and one of them practical, bringing quantum machine learning into numerically investigating what process matrices can do. And now I'm happy to take questions if I still have the time. Yes? Here? Yes, yes. So, first of all, the time that an agent A uses is their own proper time here. So they are using the actual time that they are perceiving. Secondly, just as usual in quantum, in process matrices, we demand all unitaries, not just some. And secondly, what is shown here is a specific scenario, but how should I say, it's necessary but not sufficient in the sense that the agent D here is sort of localized together with A, because A sees these operations happen on a specific localized system and not being sort of spread out over different systems. So this doesn't model agents that have their own proper time being in superposition with respect to all the other old agents. Like, this is strictly necessary but not sufficient. And the idea here is that if there are many causal reference frames in principle that can describe the same process, but we demand sort of the true one. We want to have the true one that's really going on outside in nature. And if this is the correct causal reference frame to use, then it should be possible to insert an agent like that. Yes, exactly. Like the postulate would say, there has to exist a causal reference frame decomposition for each agent that allows to do this. Yes?
Well, it's motivated by the title, the expression. So in this work, can you somehow distinguish if it is some time dilation due to some special relativity proper or some quantum space-time? So with this formalism, can we learn something about space-time being flat or not, or quantum or particle, or it is like blind for this question?
That's a very good question. And so, as I said, there are notions of time dilation effects and time dilation effects in superposition, which we actually showed for controlled superpositions of quantum Krumms. The important part here is that we are freezing some clocks to achieve these superpositions of quantum Krumms with different orders. So we have this part of relativity, or this part of, let's call it curvature, because the ticking rates of the clocks dynamically changes. But what we do not have is a relativistic modeling of space, because we still are looking at circuits. So essentially our notion of time here and the classical perception of proper time is really just a circuit picture.
Thank you very much. Let's thank again. And so now, the next speaker happened that he is acting trouble, and it's on call, it's online, and actually we are late, so this is the argument time of the talk. Just some more, 5 minutes so that we can contact the speaker for
Can I?
for the next talk. And so, meanwhile, let me just remind you about myself. So again, this is the time you to have requested responding for positive. You cannot have it, you don't sign. And another thing is that we will have the conference photo after this session. But since we are going to have 5 talks and the other room are going to have 6 talks, it might be a bit not directly after hours. So just hold and wait in the corridor until we have the time for the photo. Just don't forget
gonna try to please come on the stage, but let's wait the other people because we have to do the photo.
Oh. Sorry, I have to get out. Master student who is watching online about me. I forgot this.
Yeah, thanks. Sorry, I should have reminded you.
A master student who is watching online just told me.
Perfect. I hope you didn't tell anything problematic.
Italiano. può dire qualcosa, per favore?
Can you see the slides?
So this is the microphone.
Can you see the slides?
Yes, so we can. Just one technical thing. Can we just remove that thing? There is something in front of. Yeah. Okay, got it. So
Can you see the cursor?
Yes, we can.
Okay.
So our next speaker is Paolo Bertozzini, and with modular theory, quantization, and the non-computative space-time. Please go ahead, Paolo.
Thank you very much, especially to the organizer for giving the opportunity to join this event and present these ideas. These is an old idea, maybe older than 30 years old, that is still not completely working, but I hope that it has some meaning. This is the list of collaborators and ex-students that have been working a little bit or partially or intensively on these things. So modular algebraic quantum gravity is an attempt to get non-commutative geometry from states via modular theory. So it goes in a contrary direction compared to most of the approaches to quantum gravity, where people are recovering geometry as an emergent thing. So we are asking if it has a meaning to talk about geometry at the quantum level. If there is a message that you want to take home, you take home from this slide. Okay, so the usual procedure is to go from geometry to dynamics and to equilibrium states, at least locally. So you start with a classical space-time, and for example, you get free geodesic motion that give the dynamics. And if you have a suitable algebra of classical observables, you can check that there is an equilibrium states that satisfy a classical version of equilibrium Kubo-Martin-Schwinger equilibrium property. We are interested in the reverse direction to go from states to geometry. So we are interested to start with quantum algebras of partial observables and states over them, use the modular theory of Tomita Takesaki to get a quantum dynamics, and then from quantum dynamics to get a quantum space-time finally. In 2010, we wrote a preliminary work where we got stuck here in the middle, so we obtain a non-commutative geometry at the level of phase space. So we get some version of phase space spectral triples, where in place of the Dirac operator, in the case of Alencon, we get the modular generator. But from this phase-space geometry to get to quantum space-time geometry is something that is not yet viable. So we have been trying this kind of reverse engineering, trying to see if we start with a classical space-time, if we can get some more information on how finally doing this circuit we obtain a modular quantization of space-time. The main features, in case there is no time enough, is that there is a modular localization, so quantum subsystems are identified by their KMS equilibrium property with respect to a state. So this is what we define as quantum subsystems. There is a notion of generalized equivalent principle, so essentially all the interactions are subsumed into the geometry that in our case should be more general than a Lorentzian manifold. Tomita Takesaki modular theory that is usually described as a version of non-commutative measure theory in the typical approach to non-commutative geometry is actually strictly related to complexification of orthosymplectic spaces. We will see this in a moment. The key features that we have that are somehow unexpected is that these approaches are equipped with a canonical CPT symmetry that is always there. And we discovered that they are also equipped always with a canonical modular Born geometry that is a doubled version of what people call today Born geometry. And specifically, there exists an operator that is the Born reciprocity. What is the motivation for these things? Typically, people consider quantum field theory. And although interactive quantum field theory is not rigorous yet, people are still convinced that free quantum field theory is safe. Well, we are going to challenge this. You start, for example, with Minkowski space-time, and you take a double cone, and you consider the Klein-Gordon equation for the scalar field. You get a symplectic space of solutions, and then taking a second quantization, you obtain the Weil algebra of maybe the exponentiated Weil algebra, and you obtain an algebraic quantum field theory that is described in this way. What is strange about it is that we have this very famous Risch-Leader theorem, the Weil algebras that are obtained from every local region, for example, a double cone, are equipped with a one-parameter group of automorphisms that come from the vacuum vector in the Fock space that becomes a cyclic and separating vector. So essentially, the vacuum vector becomes thermal for every local algebra. Of course, for some special local algebra, this has been interpreted, and it has been discussed in this meeting several times. Unfortunately, it is a mystery since the 70s to interpret the geometrical and physical meaning of this one-parameter modular group. We conjecture that this one-parameter modular group that cannot be interpreted on the standard geometry of Minkowski space or Lorentzian manifolds is due to some non-commutative geometry that is in the background. For those that do not know Tomita-Takesaki theory, this is a short introduction. You have a von Neumann algebra that is an algebra that is equal to its double commutant, and there exists a cyclic separating vector inside the Hilbert space. The cyclic separating vector assures that there exists a one-parameter unitary group that is preserving the algebra, so there is a canonical dynamics on the algebra, and there exists a conjugate linear isometry that is mapping the algebra to its commutant. It is much less well known that actually modular theory is not only limited to the category of von Neumann algebras. It is actually rooted in something deeper. There is a, let's say, first quantization version of modular theory that is related to the existence of a one-parameter group of unitary that is preserving a real subspace that is in standard form inside the Hilbert space. Actually, what we proved is that this theory, that is the first quantized version of modular theory, is not really about Hilbert spaces in itself. It's something that is related with complexification of orthosymplectic space. So if you have a real vector space equipped with a metric and with a symplectic structure that satisfies some compatibility condition, automatically you get standard real subspaces of a Hilbert space, and so the modular theory is unleashed. So modular theory is deeply a theory about the interaction between the metric and the symplectic structure. So what I mean by quantization, usually people, when they talk about quantization, they think about let's say, second quantization functor. You have a physical system that is determined by certain degrees of freedom. In our case, it would be, for example, a symplectic space. And we apply the second quantization functor and we get the Weil algebra. Or we apply a classical functor that, for example, gives certain observables that are, for example, the symmetric algebra on the vector space. And then there are the quantization and dequantization maps that are linking this classical and quantum version of the system. What we stress is that usually people consider only the symplectic structure. Here, the extremely important ingredient is the metric structure also, because modular theory is originating from the interplay between the metric structure and the symplectic structure. A typical case, as you see, I start with a symplectic space, I get the Weil algebra with the second quantization functor, and I get the symmetric algebra, and here is the Weil quantization and the symbol, the quantization maps. Here is how the Weil algebra, this one is the unbounded one, okay? So it's not the exponentiated form. If you have a symplectic manifold that is the cotangent space of, for example, a Riemannian manifold, there is a nonlinear version of these. You take your cotangent space and you get a second quantization that gives the differential operators over X, and you get a classical functor that give you the algebra of symbols, and this is the same Weil the quantization map. What happens if you have a metric apart from the symplectic structure? First of all, the metric induces a canonical polarization. So the tangent space to the symplectic manifold splits canonically in pairs, and there exists a real structure that is reversing the sign of the momentum. And there exists also a canonical Born symmetry that comes from the Ries duality. So every vector gives a covector by Ries duality, and you use the Ries duality to define a Born symmetry that is a complex structure that anti-commutes with the real structure that comes from the polarization. Not only, this is not the extremely interesting thing that happens when you add a metric. Magically, you get modular theory associated to every Riemann manifold. You get a Riemann manifold, you consider the metric, you consider the Gualtieri generalized tangent bundle, that is just the sum of the tangent bundle and the cotangent bundle, and you complexify it. The generalized tangent bundle is a real subbundle in standard form inside the complexification. And so fiber by fiber, we can unleash modular theory. And so there exists a gauge group that is acting on this complexified, generalized tangent bundle. What is the physical meaning? We don't know exactly completely what it is, but we notice that the thing is resembling having two copies of the Riemann manifold that are in dualities through a Ries isomorphism at the level of the tangent spaces. And we notice that the modular flux that we just identify on a Riemann manifold is actually acting on the complexified of the Tulchiev bundle. For people that are familiar with classical mechanics, they know that the Tulchiev bundle is the stage where you discuss dynamics in classical systems that are subsuming both the Hamiltonian and the Lagrangian approach. So the dynamics can be described as a distribution on the Tulchiev bundle. So it's interesting to see that our modular flux is probably related to a dynamics in implicit form. This is the most technical part of this talk, and we have been able to generalize what we just found. If we start with a general orthosymplectic space that doesn't come from a polarized one, so we don't have a polarization here. If we consider the modular structure associated with the complexification of this orthosymplectic space, we consider the generator. This is the modular Hamiltonian that generates the modular one-parameter group. We do the polar decomposition, and we observe that we get for free a modular Born symmetry that lives on the complexification of V that is obtained taking the multiplication by I of these grading operator that come from the polar decomposition of the modular generator. This modular Born symmetry is exactly coinciding with the complexification of the polar decomposition of the polarizers of the orthosymplectic space. The polarizers are the two operators that relate the metric and the symplectic structure that come from the Ries duality theorem. So every symplectic structure that is continuous with respect to the metric can be obtained through the action of an operator P. And you use the polar decomposition, you obtain here a complex structure B, you complexify the complex structure, and you obtain this modular Born symmetry. Amazingly, this J modular conjugation, phi modular Born reciprocity. And the multiplication by I generate on the complexification the action of an hypercomplex algebra that is the real algebra of the qubit. So you take the qubit algebra considered as a real algebra, as an hypercomplex algebra, and canonically on the complexification of an orthosymplectic space, there is always this double Born geometry that we call the modular Born geometry. What we conjecture is that what we miss is a real polarization on the complexification. When you have a classical geometry, so you are starting with a polarized situation in the orthosymplectic space, the real polarization allows you to identify the Weil algebra in the double as differential operators on a manifold. When we conjecture that when we are in this not polarized, not classically polarized situation, we still can achieve quantum polarization using the operator gamma. And this should identify some configuration non-commutative space and identify the Weil algebra as an algebra of differential operators on a non-commutative algebra in the sense of Paschke and Kopf. This is a paper that was written some time ago by Paschke about non-commutative configuration spaces.
Paolo, just a quick reminder, we already reached 15 minutes of your talk.
Yes, I want to stop alerting about possible experimental verification of these things. I'm sure that people here have been aware of the GQuest and similar experiments. So these are experiments that are measuring the fluctuation of the modular generator. So if some positive answer is obtained here, for sure it is a partial confirmation of our hypothetical role of modular theory. The most important message, that is the final message that I want to leave, is that in our opinion, this point of view is a quantum justification of the cosmological models of Boyle and Turok about CPT symmetric cosmologies. The Boyle-Turok model at this moment is semi-classical. But in our opinion, the existence of a canonical CPT and the existence of thermal representation that are always reducible factorial, okay, is a strong indication that our universe has always a CPT symmetric copy of it. So this should be a quantum level justification of these models, I suppose. For people that are interested, the file is available. This is the list of papers that are inspiring the work. There are many others coming out. Thank you very much for your attention. Hello?
We have time for one quick question. Do we have?
So I saw something which I thought was interesting in your PowerPoint. If you go back a few slides, it was about if you have a Riemann classical geometry, then you said canonically identified to, if you go for, yeah, I don't know the exact statement.
Sorry, can you repeat? Can you repeat? Because the sound is a little blurring. Hello?
Can you hear me?
Yes, can you repeat the question, because the question was a little bit blurred. I could not hear.
Yeah, sure. So you made a statement about canonical identification for Riemannian classical geometry. It was like a few slides back.
Yes.
Maybe this is a standard result in the literature, and I'm just not more aware. But just one more. Yeah, here we go.
No, as far as we know, it's not known.
Yeah, so you say here, a Riemannian classical geometry, if this canonically identified gauge modular flows, but is that from like, how do you obtain this modular flow?
I obtain exactly as I say before. The modular theory is not only related to von Neumann algebras. It comes in a first quantized version as long as you complexify an orthosymplectic space, okay? So I take the Riemann manifold, I take the tangent space, that is a space equipped with a bilinear symmetric form.
Yeah.
I take the Gualtieri generalized tangent bundle. This one is a symplectic space, fiber by fiber.
Right.
And if I take the Ries dual metric on the cotangent and I make the direct sum, I obtain a metric on these complexified, okay?
Yeah.
And so I obtain an orthosymplectic space. This is an orthosymplectic space fiber by fiber. If I complexify it, I get modular theory. There is a technical point. You have to consider this parameter a little bit less than 1.
Right.
Otherwise, if this parameter is either 0 or 1, you get that this real orthosymplectic space is a Keller subspace of the Hilbert space. And the modular theory either get frozen or it diverge. Okay, so these are singular situations for modular theory. But as long as you take this parameter in front of the symplectic structure, and this parameter in front of the complex structure of the symplectic structure is in this range, then we have modular theory that is canonically associated fiber by fiber. So there is a gauge modular group that lives in the complexified of the Gualtieri generalized tangent space.
Thank you. I wasn't aware of that. Thank you.
You're welcome.
Thank you very much. Let's thank the speaker again.
So let's hurry outside to the staircase, the white staircase.
Our next speaker is Fedida from University of Cambridge, and he's going to talk about foundations of relational quantum field theory.
Great, thank you very much for the introduction, and thank you to the organizers for this lovely event. So this is work in collaboration with Jan Glowacki from ICOCI Vienna, and we're asking a question, right? Can one of the most absolutist theories of modern physics, so quantum field theory, where you have these objects, these things that exist over all of space-time that you probe, that they really exist in an absolutist manner, can you understand them relationally? Okay? Now, there's a lot to say, and I will only be able to present a subset of results, so bear with me. Okay, so we start with a thought experiment. Imagine you are preparing an experiment, okay, a quantum experiment. So you have a quantum system on a table, like this phone, that you describe relative to a classical reference frame for now. So a ruler and a clock, okay? Formally, a ruler and a clock are elements of a Lorentz frame bundle, okay? Now, imagine you have the bad luck of having me as an experimentalist colleague because I'm very clumsy. I bump into your table and I tell you, oh, I'm so sorry, I think with probability P, nothing happens, but with probability 1 minus P, I think your rulers and your clocks moved to a different location and maybe got boosted, rotated, etc. So really, I could generalize this further by saying I give you a whole probability distribution over the space of frames, and really now you have a proper mixture, okay? And the statistics will follow this proper mixture if I keep bumping into your table. As I said, I'm really clumsy, so that's what I do infinitely many times. Okay. All right, now if you choose an origin in your space of frames, you can rewrite this proper mixture as follows. And now we do a small, I think, physically motivated leap, which is to say that the expectation value of an operator phi, okay, scalar operator, with respect to this state, which is described relative to the shifted reference frame, is related to the expectation value of the same phi with respect to the state in the original reference frame through a unitary transformation. You can think of this basically as saying, when I apply the rotation and the boost, maybe, it's equivalent in some sense to saying I have moved and rotated the system in itself. Okay, at least at the level of expectation values. So that gives us a weakly continuous unitary representation, unitary action of the Poincaré group on the bounded operators, the left action, and so right action on the dual. Okay, and so by associating this identity in the space of frames, we can actually go into a Heisenberg-like picture, if you will. And so the operator that you should consider in this thought experiment is given as follows. Okay, we've abused notation, and it's non-trivial, but you can write this down more or less. Okay, now you make another logical leap, and that is to say that every physical system is fundamentally quantum mechanical, and that your reference frames are themselves quantum mechanical, or physical, if you will. That leads to a notion of quantum reference frames, okay? So you have a Hilbert space, covariant P of EM, okay, over the space of frames. You can think of this in simple cases as a clock which is covariant with respect to the reals. Okay, here we have clocks and rods in the space of frames, so really it's a tetrad that can be acted upon by Poincaré. And so you have a quantum reference frame, okay? So your P of M represents your quantum clocks and rods. You can prepare your P of M or your QRF in a certain state, okay? So really taking this Born probability measure amounts to localizing in the space of frames your quantum reference frame. And if you make this logical leap, and instead of saying that I, as a classical agent, keep bumping into your table, you can say, well, fundamentally, the operator, the object that you want to describe, is fuzzy in the sense that it is described relative to a quantum reference frame. Okay. So this, if you're aware of the quantum reference frame formalism, this is formally the restricted relativization of phi. Okay. All right, so now a few definitions. Quantum fields are maps, okay? You can define these Lorentz-oriented quantum fields and these absolute quantum fields. And you have this covariance property, okay? So if you act on the level of the Hilbert space, you get basically your operator, which is shifted in the sense of your principal bundle. Okay. Now there's very important subtleties here that I don't really have the time to go over, but you don't have Poincaré covariance pointwise, and this is very good because otherwise you would go into a no-go theorem by Vezemirsky. But up till now, as we see, we integrate over Poincaré or over the space of frames. But when we think about quantum field theory, axiomatic quantum field theory, especially Weizmann quantum field theory, you actually smear quantum fields over space-time. So what's going on? Okay. Well, now we can use some tricks from mathematics. You can disintegrate the measure over Poincaré into a conditional measure and a marginal measure. Now, it turns out your marginal measure can be written as follows, using the marginal P of EM, which is also provably Poincaré covariant. And your conditional probability measure also has certain important properties, and then you make an important definition. A relational scalar quantum field is a map from Minkowski to bounded operators, which is given essentially by the averaging of these Lorentz-oriented quantum fields, absolute quantum fields, over your fibers, over the Lorentz orientation that you don't have access to. Okay? And now you can write down your relational local observables. So these are scalar relational local observables. You can do spinners, but it's a bit more involved. As a smearing of these relational quantum fields over space-time. Okay? And now we have a theorem that is covariance. So really, we have covariance under the integral. Now, there is also an important subtlety here that the relational quantum fields are shifted as well in terms of a localization. This is important. Otherwise, you would fall into definition problems. Please ask if you're confused. Okay. So we have these quantum fields, but can we make contact with Weizmann quantum fields and other approaches to quantum field theory? There happens to be also a lot of links you can make with algebraic quantum field theory, but here, let me focus on Weizmann. So in Weizmann quantum field theory, you have quantum fields as maps from Schwartz, the Schwartz functions, okay, to unbounded operators in general, and you can only morally write them as the integral of an absolute quantum field smeared over space-time with these Schwartz functions. So Schwartz function is like a smooth function which vanishes very quickly at infinity. So we can make contact with this formalism by saying, I have a map now from states in my reference frame, Hilbert space, to bounded operators in the system Hilbert space that I define as follows. Okay, and now we have a notion of covariance which is essentially identical, especially once we consider the special case of a certain class of quantum reference frames over this principal bundle, where we say if this marginal Born property measure has a Radon-Nikodym derivative with respect to the Lebesgue measure, which exists and is Schwartz, then we can really write in the same sense as Weizmann, and the covariance is precisely the same. Okay, so this is nice. And actually, we can do more. We can talk about causality as well. Okay, so we can talk about Einstein causality, and really this Weizmann comparison propagates quite far. Okay, we can even do better. We can do something which is really hard to do, for example, in Weizmann quantum field theory, which is to impose microcausality pointwise. Okay, there are no-go theorems that tell you if you have translation covariance quantum fields pointwise, then you cannot impose microcausality if your Hamiltonian is bounded from below. But here, the relational quantum fields are not translation covariant, pointwise. So really, we can make contact as well with some physicists' QFT. Okay, you can define now time-ordered correlation functions, and so on. Okay, we can also define vacuum expectation values if you assume that there exists a Poincaré covariant state. Okay, you can define your Weizmann functions, and basically we recover all the Weizmann function properties. So really, we can make a very strong contact with Weizmann. Okay, that leads me to the conclusion. Basically, we get a natural notion of relational scalar quantum fields. These, I must say, there's the interesting caveat that they are bounded, okay, because it's somewhat more operational, unlike Weizmann. We get covariance under the integral. We can discuss causality, statistical independence, which I didn't quite go over. Vacuum expectation values have the same properties as Weizmann. Spinors can be recovered if you take the universal cover of the Lorentz group. We can discuss relational Lagrangian densities, relational Hamiltonian densities, and relational actions. And there's a lot more to do, okay? The paper should be out any day now. So stay tuned for that, and please ask if you have questions. Thank you.
I have a question. It's a general question I normally have about quantum reference frames. So when you think about, I think you didn't talk much about measurement, but probably it's hidden somewhere there. When you think about a measurement, are you thinking like in quantum mechanics, where you have agents, where he's a person, well-defined measurement, or is your reference frame making the measurement?
Okay, yeah, this is a great question. We try to avoid talking about agents at this point. And indeed, we are not forced to take, to impose an ontology which is, for example, relational. We don't say that agents are those systems which carry a quantum reference frame. We could, and maybe this is a natural notion of agents. Okay, so you could say, I describe as an agent a system, and relative to me, it looks smeared like a quantum field. I think this is a bit too soon to discuss this sort of things, but yeah, so hopefully that helps.
Okay, thank you very much. Any other question? So let's thank the speaker again. And a general request for all the speakers, when we are in the question time, feel free to already come and set your computer.
Perfect. Where does this go? Here.
But this is for the audio. You need also the pointer?
Sure, yeah.
Speaker is Paiva from the University of Bristol with unitarity, non-unitarity, and choice of clock observable in the page-Witter's framework.
Thank you. Yeah, so as Natalia just said, my name is Ismael. I'm current at Bristol, and I'll be talking about this project I've been developing in collaboration. Okay, is it better? With Czesław Bruckner, Jelena Gurianova, and Max Locke. We'll be giving another talk about page routers. It will be 3 talks after mine, so stay tuned. It's about the issue of non-unitarity that appears in page routers framework. I will explain everything in the next few minutes. And then for us, this is an issue, and then we are trying to find a way to kind of remove this and to see if we can overcome it somehow. And that's the main question of this project. And I start with this sentence time is defined so that motion looks simple, because this is really behind, it's the main philosophy behind our work. But yeah, I'll be talking about page utils, and then I'll be first do a short introduction. It's a framework that was introduced because of this Hamiltonian constraint, the Wheeler-DeWitt equation, which basically tells you that the total Hamiltonian of the universe, say, applied to your wave function, should give you 0. So the wave function should vanish if you apply the wave function. So the Hamiltonian to it. So like time, in principle, the system does evolve in time, right? So how can we recover our standard notion of time evolution that we observe in the labs and that we experience every day, in particular the Schrödinger dynamics. And then what Page and Utils did is like they split the system into 2 parts. One they wanted to use as a clock system that would be used as a reference to study your system S, like the rest of the universe in this case. Just so we keep track, so now that we introduced these 2 parts, we have this kinematic Hilbert space, but it's too large. The actual physical states, they live in a smaller subspace, let's say, without entering technicalities, of this kinematic Hilbert space. And in particular, the physical Hilbert space doesn't really have the tensor product structure, because we only care about states that satisfy the constraint. So, okay, so far the clock system is just another system. We want to endow it with an observable that will be like our clock observable, our time observable. But before they introduced this Page Utils said that the total Hamiltonian would be a linear combination of the free Hamiltonian of the clock and the free Hamiltonian of the system. The free Hamiltonian of the clock, for simplicity, we will assume that is non-degenerate in this talk. And then they defined what we can do in general, in more modern approaches even, is to define a subset of states that are translated by the Hamiltonian, the free Hamiltonian of the clock, and construct a POVM with it. So this POVM is called a covariant POVM with respect to HC. It's a mouthful, but the covariant term here means just that the time states are translated by HC. So now that we have this POVM, this will be our clock observable, and then we really have a clock. And then we can look at the system by doing conditionings on time states, and this will be the state of system S at time t. And then we can write, the joint state of the system as this history state, as it's called, because it contains the entire history of system S. And if you take the derivative of psi s, you get the Schrödinger equation, which was the objective, so we can recover the standard dynamics. Now, in general, we want to include interactions. Okay? Yeah, in general, we want to include interactions for a series of reasons. For instance, well, in a gravitational scenario, you imagine the systems will interact, or even for operational purposes, because you want to use your clock to control things in your system. And we do it, and typically the way people do it is like they use the same definitions, and then we have the same structure, but then we get a generalized Schrödinger equation. It's a Schrödinger equation, but then with this extra term that can be even time non-local. The issue is that sometimes you can get non-unitarity. So depending on the interaction that you have, you might, for instance, H, you get unitarity, so you have all the symmetries and it's very nice. However, with some interactions, you might get non-unitarity, so the norm of your vectors or even the angle between them won't be preserved in the dynamics. So for instance, just to give a quick example, if your interaction is of this type, OS tensor HC, the extra term becomes proportional to this time derivative, and then when you get the Schrödinger equation, you are led to this term, to this expression, And if OS doesn't commute with HS, this is the effective Hamiltonian is no Hermitian, and then we have no unitarity. Now, just to give very briefly, a concrete example from this article, if you have a massive system that's traveling with an internal clock and there is no acceleration, you get a unitary dynamics from the perspective of your clock. However, if the system starts accelerating and you use the energy mass relativistic correction, you get an effective interaction between your system, your internal system, your clock, and your external degrees of freedom of your system, and then you get non-unitary relational dynamics, even though you initially didn't have an interaction per se. So, yes, this is the issue of non-unitarity also appeared in some other works, for instance, in measurement scenarios, in the first two works, and also in this final work, in which a bigger analysis of when the non-unitarity depends or not on the internal structure of the clock. Whether or not it depends on the internal structure of your clock. Now, so let's go back to the original sentence, like time is defined so that motion looks simple and non-unitary, as I mentioned, if you don't have unitarity, you don't have some nice symmetries that we'd like our theories to have, like the angle between vectors, and you can even come up with examples in which the state of system S becomes zero, like the norm becomes zero in an instant of time, and then it returns to some finite value, finite positive value after that. So it's really like undesirable. And then we started asking ourselves, like, but do we really need to accept non-unitarity and understand it as a consequence of the interaction, or is it a consequence of our clock observable? So in particular, maybe with the standard choice of clock observable, we have, we have no unitarity, but then if we change the clock observable, we might be able to see unitarity. Then to see if this idea makes sense, we went back to the scenario without interactions. But then this time we are writing the free Hamiltonian of the clock as hc plus hc primed. And then but the time states are covariant with respect to hc only, not hc plus hc primed. And by doing so, when we get to the Schrödinger equation, we get to the generalized one. We have this extra term, that's time non-local. And depending on how you do the partition hc plus hc primed, you can get non-unitarity. Because hc prime is pretty much playing the same role as the interacting term before. So we saw like, oh, it makes sense that the choice of clock observable can really influence whether you see unitarity or not. But then, to actually confirm it, we thought of an example in which the system is a qubit and the clock is a Q-treat, and there is this interaction between them. In this scenario, the physical states are of this form, any generic physics state, and if you use the standard clock observable, we can write it in this way. It's pretty much a linear combination of eigenstates of the free Hamiltonian of the clock. And as you can see, in the subspace 0, 1, it's like a sigma x. So the eigenstates are 0 plus 1 and 0 minus 1. And then we have 2 in the other direction. But then, once you look at the state of the system at t, that's the expression you get. So you see that it's not unitary. However, if you define your time state like in this way, when you look at the system, you'll see a unitary dynamics. So there was a different clock observable that you could use that would allow you to see unitary dynamics. And based on this example, we managed to actually get to our result, which is a series of statements that are equivalent, and there are presented 3 of them. The first is that it's possible to get unitary dynamics. If it's possible, it's equivalent to say that if you take the partial trace over your system, so you just look at your clock, and you diagonalize the local state of your clock, the basis that diagonalizes it is independent of your choice of physical state. So for any physical state, your clock system is diagonalizable on the same basis. And then the other is that in this basis, the relation dynamics will be unitary. So you can build a clock observable that's covariant. This is a mouthful here. It's covariant not with respect to HC, but it's covariant with respect to Hermitian operator that's diagonal in this basis, the same basis that diagonalize rho C. You can get unitary dynamics if you build this clock observable. And then just to summarize, the non-unitary in the page-rooters framework can be associated with non-covariant clock observables. In some scenarios, unitary is manifested only with non-standard choice of clock. So if you use the standard choice, you will see non-unitary dynamics. However, it's not always possible, which if you see, like us, if you believe that non-unitary is an issue, this is a breakdown of the page-rooters framework. This work will be soon on archive, fingers crossed. And with that, I thank you for your attention.
Questions? So I have one. By the way, the next speaker, it's online, right? Okay. So this result of yours, are you concerned more on how practically I can construct a clock, or on the foundations of time? How do you distinguish time and clock in your formalism?
Well, we have a generic clock, so we are not like constructing a physical model. We have the clock observable that we put inside our framework, and then we use it as a reference for time. But which system would it actually be represented physically? We don't know. And actually, the kinematic Hilbert space, so the clock and the system, they don't really exist. What exists is the joint state that doesn't have the tensor product structure. So they are not separable. So it's even complicated to give like a more direct answer to that, because there is a lot of conceptual issues. Like, for instance, we build a clock observable, so we have these time states, we do these conditions, but this is not really a measurement. So there is a lot of questions, conceptual questions in this framework.
Okay, thank you very much. Is there any other question? If not, then let's thank okay, there is a question. Okay, sorry, I didn't see you. Let me give you the microphone.
I was thinking, if there is this trade-off between clocks and unitarity, maybe you can define some object which would take into account both, like so you can define some object that takes into account both unitarity and clocks and speak something, like create something like that.
So you mean like a different factorization?
No, I mean, can you combine them together into one, I don't know, inequality or what?
So you want this kind of the system tracking its own time in a sense? Yeah, I don't know how to do that. Because typically in a reference frame, you have a system tracking other systems, right? And it's similar with page routers. It's really a reference frame for time, but then you'll be tracking the dynamics of other systems. So yeah, I mean, but we can discuss. It would be interesting to find a way out of page routers.
Okay, so let's thank the speaker again. And the next speaker is Michael Suleymanov. I'm sorry, I think I spoke your name wrong. You can correct me. From Bar-Ilan University in Israel, with relativity of quantum correlations, invariant quantities, and frame-dependent measures. Let's check.
Can you hear us?
Can you tell something, Michel, so that we can test your audio? Okay, yeah, it's perfect. So it's outside there? Okay, so you can start, please.
Okay, so I want to thank the organizers for this opportunity. And today I want to tell you about the relativity of quantum correlations within the framework of quantum reference frames. 1 second. Oh.
No,
Yeah,
it's
okay.
not happening. Okay, now it's working.
Okay. So I'm going to start with the definition of quantum reference frames. Actually, I can do it very fast because I'm sure people already talked about it. And then we're going to focus on transformations of position momentum moments between different quantum reference frames. And as a consequence, we will see that these correlations do depend on the reference frame, and Robertson-Schrödinger position momentum uncertainty relations, and the subsystem purity. These are all perspective dependent. Then we're going to talk about the invariant quantities related to the total covariance matrix and some kind of entanglement criteria and evolution of quadratic Hamiltonians. And finally, I would like to tell you about the Stokes-Hurwitz-Piron theory as a candidate for relativistic space-time QRFs. Okay, in non-relational quantum mechanics, translations and Galilean boosts are determined by classical parameters, and in these scenarios, the position momentum moments are invariant. It includes variances and correlations and uncertainty relations and covariance matrix in general. As I told you, in quantum reference frames, it's not the case. So a quantum reference frame basically assumes that any reference frame should be treated as a physical system. And if we assume that quantum mechanics is a fundamental theory of the universe, then this physical system serving as a reference frame should be quantum. So we start with the tensor product of n particles, and then they claim that the only relative distances really have a physical meaning, which reduces the total tensor product Hilbert space to a physical one. The next step is to choose a reference frame by simply choosing the origin as one of the particles. Such a perspective dependent state satisfies the Schrödinger equation with the modified, with this kind of Hamiltonian, which reduces to the standard quantum mechanics where the mass of the reference frame is much bigger than the others. These results are known. We use here the perspective neutral quantum reference frame approach introduced in this paper below. So what we show in our paper is that two different quantum reference frames, I and J, they can describe each other. And in this case, they do agree about the position variance. They do not agree about the momentum variance. When describing the third particle K, the situation is opposite. They agree about the momentum variance, but not about the position variance. And they can also describe a correlation between any two particles K and L, both momentum, position, or mixed ones. And the mixed ones, you can see that they're not the same in different reference frames. What we can see, the transformation of that includes the variances and the correlations, looks exactly like the triangle law of cosines. You can see the analog picture here, where the sides of the triangle are the position variances and the angles are related to the correlations. So the correlations actually acts like a cosines, and that gives us all the triangle inequalities from geometry. I just picked two from them. So of course the triangle inequality related to the sides, to the variances, and the correlations. For example, the sum of the correlations has to be positive, and it's bounded from 1 to 3 halves. Okay. But what if we consider a very specific scenario as a limit what if one of the variances is very small compared to the others? Or we can say that I and j see each other as perfectly localized. So in this case, you see that the variance of k from both I and j perspectives coincide in this case. The correlation of I and j is maximally equals 1 in all reference frames. And basically can say that such reference frames that see each other perfectly localized are equivalent at least up to the second moments. That gives us back the non-relational quantum mechanics case when the reference frames do agree about the second moments, especially uncertainty relations, and of course about the determinant of or the covariance matrix and its determinant. The next slide, you will see why I mentioned determinant of the covariance matrix. Now I want to focus on a subsystem purity. So imagine that I and j describing a big system, and how will the purity of subsystem K will look in different perspectives. So in general, as I showed in the previous slide, the second moments do not coincide in different perspectives. So in general, I and j will not agree on the purity of subsystem K. But of course, for equivalent QRFs, the purities are the same. But in general, it's not the case. So next, I want to move to the invariant quantities. First one is very simple, but very interesting and important, I think. The variance-based entanglement criteria introduced by Reid, Duan, and Simon. There are two kinds of them: the product and the sum, and these are EPR-like tests. As I already showed you, the second moments concerning the momentum are the same in two different QRFs, but the position one is not. But we do not need the position, we need the difference. And the difference is really independent of quantum reference frames. So different quantum reference frames will agree about the variance-based entanglement criteria, which means that if the systems K and L are entangled according to this criteria, both QRFs will agree on that. We know that the entanglement in general is perspective dependent, but this specific test is not. Next, I want to talk about the total covariance matrix. So the individual covariance matrix, as we saw, is perspective dependent, but the total one is not. The transformation between the total covariance matrices turns out to be such that the determinant of this transformation matrix theta is 1, which means the determinant of the total covariance matrix is the same in all perspectives. So we can see here that A describes all the system including B, and the second scenario, they switch roles. In both cases, the volume, the uncertainty volume that corresponds to the determinant of the covariance matrix is the same. The shape might be different. In one system, we can see separated particles, and the other it does not have to be this way, but the volume will be the same. Okay, next I want to talk about a specific case of interactions. So if we have a quadratic Hamiltonian, the covariance matrix, total covariance matrix in this case, the evolution of the total covariance matrix is given by symplectic matrices S. The determinants of or the product of the determinants of S is 1. So in this case, the determinant is constant in time. So the determinant of the covariance matrix is also constants in time, and QRF invariant. And next, this is a preliminary results. Like this, it's my next project. I just want to share with you first thoughts. I have a few minutes, right? So, when we talk about spatial and temporal QRFs in non-relativistic quantum mechanics, there are a lot of papers about spatial, temporal, and the combination of them. There are also space-time relativistic quantum reference frames. Of course, the ultimate goal is to do it in the relativistic quantum field theory, but I think it's very useful to try to find consistent many-particle relativistic quantum mechanics, and I want to suggest one such a framework. So this framework is called the Stuckelberg-Horvitz-Perron theory, SHP, in short. And this it was suggested by Stuckelberg in 1941 as a classical toy model to describe a electron-positron annihilation. So in this theory, there's a universal world universe time, tau, and which parameterized the world line of the particle. And Stuckelberg claimed that due to interaction, this world line might bend, and it can go backwards in time. The measured time, right? We cannot measure the universal time, just like the time in Newtonian mechanics or in non-relativistic quantum mechanics. But what we can measure is t, and according to this measured time, particle goes backwards in time, and it's equivalent to antiparticle going forward in time. Okay? This framework has a quantum version. It was later generalized by Horvitz-Perron, Arshansky, and many others. So it goes like this. Imagine that we have this kind of Stuckelberg-Horvitz, Stuckelberg-Schrödinger equation. I cannot see my mouse. 1 second. Okay, doesn't matter. In this kind of theory, of course, the time-energy associated relations are automatic, just like the position momentum. And we can formulate the QRF framework in this theory, relational picture. So again, we will have a space-time translation invariance. We can choose a quantum reference frame by choosing a space-time point, like you can see in this figure. And now, what you can really measure is the time and the position of any quantum system as a measurable quantity. So here you have two different probability distribution related to some particle I, and different tau. What you really can measure is the expectation value of x and t, and that's related to the position and moment, the position and time with respect to the reference frame. Okay, I see that I'm running out of time. I think I will stop here, and thank you for your attention. Hello? Cannot hear you.
Yes. Okay, we were in the mute. So we have one question. Is there any question from the audience? I have a quick question for you. So I understood that you wanted to connect quantum reference frames framework to relativistic scenarios. And one thing is about finding time reference frames with respect to time, right? So for instance, but let's suppose that I simply have a clock that officially in a superposition of two different, not times, but times marked by the clock. Could you please describe this clock in superposition as well? Or some clock delocalized by a genuinely relativistic effect? Do you understand my question?
Yeah. I understood the question. Actually, this framework was applied to interference in time experiments. So that's a very natural thing to do here. It's of course possible and part of the theory. Yeah, superposition in time, definitely.
So it must be something from relativity effect. I could not artificially create that. Did you hear me? Oh, I think you are frozen.
No, can you repeat the question?
I could not artificially create a clock in different states of time, let's say. Well, maybe after I ask you online. For
okay. I have an answer, but it will take some time. Yeah, you really. The short answer is you have to really integrate over all tau to see the whole picture of the universe, right? As an example with the electron positron annihilation, you really have to integrate over all tau to see the big picture.
Thank you very much. So let's thank the.
I hope that was clear.
Now we have, oh, hello. Hi.
I cannot
hear me.
Sorry.
Okay. Now we have Fabio Maria Mele from the University.
Oh, sorry.
Okay, we have, hello. Okay, we have linking quantum error correction and gauge theory via quantum reference frame.
Should I use a mic?
Maybe, no, there we have another one here. Where is it?
Oh.
Yeah.
Okay. Okay, there we go. Okay, thank you for introduction and thank you to the organizer for giving me the opportunity to present this work in this nice conference. So this work is going to be essentially about relating two different fields, namely quantum error corrections and constraint quantization and gauge theories. And it's based on a paper we posted on arXiv last December in collaboration with Sylvain Carrozza, Aidan Chatwin-Davis and Philip Hon. So if you want to summarize the key aspect of this talk in one word, that will be redundancy. And the reason for this is that redundancy is essentially the hallmark of both fields, so both quantum error corrections and gauge theories, in that you can't have quantum error correction without redundancy, because in principle in quantum error correction what you want to achieve is to encode the quantum information you are interested in a larger system in such a way that possibly whatever source of noise or error is going to act on the additional degrees of freedom, the redundant degrees of freedom, such that you can detect the errors and recover the quantum information, the quantum data you are interested in. And similarly, also in gauge theories, you actually can't have any gauge symmetry without redundancy, because typically in gauge theories, you have that not all kinematical degrees of freedom are physically relevant, but only composite operators, which are invariant under the gauge group, are physically relevant. And moreover, on the gauge theory side, you have that the encoded logical information is independent of the redundancy. And similarly, the gauge invariant information is independent of what redundant degrees of freedom you use to parameterize your gauge. And in particular, in stabilizer codes, you have that the relevant physical information is invariant under the action of the Pauli stabilizer. And similarly, in gauge theories, you have that the gauge invariant information, as you all know, is invariant under the action of the gauge group. So, and of course, here I'm speaking about redundant degrees of freedom, but the choice of which degrees of freedom are used to parameterize the redundancy are arbitrary in both contexts. And in fact, you have that even for a given quantum code, there will be many possible set of errors that you can correct for, and which one you choose depends on the practical application you are interested in. And similarly, also in gauge theories, you have multiple ways to either address gauge non-invariant quantities to form gauge invariant quantities, or equivalently to gauge fix your redundancy. And this, as we will see soon, is going to be related to the many possible choices of QRFs, which just shortly, as you already heard in the previous talks, it's just universal tools to deal with symmetries in quantum systems that are going to be ubiquitously arising when you want to construct gauge invariant relation observables. So already from this first slide, you can see that there is a clear analogy between these two fields. And so the aim of the talk is going to be to make this analogy precise structural correspondence. Of course, I cannot enter in details in just 10 minutes, so I will just give a flavor of what the correspondence is about. And as I already told you, in order to make this correspondence precise, we need to make sense of concept on one side to the other. For example, concepts like encodings, errors, and logical data on the gauge theory side, which are typically not considered in the standard formulation. And the key tool to do this are going to be quantum reference frames. In particular, we will use the so-called perspective neutral approach that was already summarized in the previous talk. And actually, let me tell that even though there are several approaches to QRFs, in this correspondence is feasible only when using such an approach, because it is essentially built and tamed on the language of gauge theory, so it's already naturally built to encode all the structure you need, as I will try to convey later. And in these frameworks, actually, what is a quantum reference frame is, roughly speaking, a choice of a splitting between redundant degrees of freedom and gauge invariant non-redundant degrees of freedom. And those redundant degrees of freedom are going to be the one that we are going to identify with our frame. So before introducing what's the role of frames, let me just start with recollecting the basic structure of both fields, and let's see how far we can go without using reference frames, and then I will introduce reference frames to fill in the missing pieces. So in both cases, you have different Hilbert spaces involved and different maps between them. So from the quantum error correction side, as I told you before, you have in principle a larger physical register, which is the actual system you want to use to implement your quantum code. And this is typically larger than the actual quantum information you're interested in. So this will contain all possible degrees of freedom, both redundant and non-redundant, and this is essentially the analog of the kinematical Hilbert space in gauge theories and constraint quantization, which encodes all possible degrees of freedom, both invariant and non-invariant. And typically, this Hilbert space is assumed to carry a unitary representation of the gauge group, which I'm going to denote by G in the following. Then, as I told you a moment ago, you are actually not interested on all possible states in this physical space of quantum error correction, but only on a subspace of it, which is typically called the code subspace. So this is actually the space which is going to actually implement the logical data you are interested in. And this will be exactly corresponding to the gauge invariant Hilbert space in constraint quantization. Namely, for finite groups, is going to be a proper subspace of the kinematical Hilbert space, which is given by the states which are left invariant by the action of the gauge group. In a similar way in which, in Pauli stabilizer codes, the code subspace is invariant under the action of the stabilizer elements. So, typically in quantum error correction, you also have a third Hilbert space, which sometimes is considered separate from the code subspace. So this is the logical Hilbert space, which you can think of it as being the abstract quantum information you are physically interested in. And this is the one that is going to be realized in terms of the code subspace within this bigger Hilbert space. Now, a priori, this is typically not obvious what is the counterpart of this Hilbert space on the gauge theory side. And here is where quantum reference frames are going to be crucial. But before going to that, let me just finish what we can say without QRFs. So here you also have in error correction, as I told you, you have errors and you want to detect them. And typically there are different error spaces, which are the target spaces of error maps, which are typically completely positive trace non-increasing maps. And these are going to bring you outside of the code subspace. And then you want to detect such errors and possibly correct to recover the quantum information, and there are well-known necessary and sufficient conditions for this to be the case, namely the famous Smirne-Laflamme condition. And at the end of the talk, hopefully, I will reinterpret this condition in terms of QRF. While on the gauge theory side, you can think of the invariant subspaces carrying the trivial representation of the gauge group. So the error spaces in the context are going to be all the charged spaces, namely all the spaces that carry non-trivial representation of the gauge group. But now we need to fill in the gap, and here is where QRFs enters the game. So let me briefly summarize the perspective neutral framework for QRFs that was already used in the previous talk for the case of temporal reference frames. Here I'm going to present it for generic groups, although in this talk I'm going to focus only on finite abelian groups, but we are currently working on also to generalize this correspondence to generic unimodularly groups. So the setup, as I said, is a kinematic Hilbert space which carries a unitary representation of the gauge group, G, and a quantum reference. So the perspective neutral approach, in essence, is a description of the physical system from within. So you want to wipe out all the external information and so describes things in a purely relational way with respect to internal degrees of freedom to the systems. So in this sense, a quantum reference frames is going to be a subsystem of your total systems, which you use as reference to describe gauge invariantly the remaining degrees of freedom. And formally, this is described in terms of a subsystem Hilbert space, which carries a unitary representation of the gauge group, which in this case can even be possibly a projective representation. And you model the configuration of the frames. So you want that the frames can be used to parameterize the gauge freedom, in particular the gauge orbits. So you want that the frame is group value itself. Fine? Okay. So this is going to be modeled in terms of a system of coherent states, which takes value in the group and carries a projective representation of the gauge group. And the frame is called ideal if the states are perfectly distinguishable, so they are orthogonal. So, and a choice of quantum reference frames is going to be a split of the redundant and non-redundant information. And for simplicity, here I'm assuming that also the gauge group is going to act with the tensor product representation, but this is a priori not necessary. So for example, if you have interaction, this is generically not the case, but this acts as Pauli stabilizer codes. And then physical states which are going to be gauge invariant, they are going to be the group average of states which are aligned relative to a given configuration of the frame. And so here you see where frames can be used to parameterize the redundancy, because as I told you, the reference frames configuration called frame orientation are parameterizing the value of the gauge group. So they are labeling the points on the gauge orbit. So you can actually gauge fix and wash away the redundancy by conditioning on the frame configuration states. And this is the so-called page-Wooter reductions that was also mentioned in the previous talk for temporal reference frames. And so what you get out of this is an Hilbert space which is isomorphic to the gauge invariant Hilbert space and encodes the descriptions of the remaining degrees of freedom after removing the redundancy relative to the chosen frame in a given configuration G. And just to give an example, for the n qubits, you have that the kinematical space is, for example, n-dimensional. You have n qubits. Then you are interested in the reference frame is going to be described by n minus k qubits. And so when you remove the redundancy associated with the configuration of this n minus k qubit, you get a space which is the reducer space, which is of the same dimension, which is 2 to the power k dimensional. And this is isomorphic to the gauge invariant Hilbert space. So they encode the same physics. But of course, you have different ways of choosing what are the ref frame degrees of freedom, and so also to condition on the orientations. And that's actually the reason why this space is called a perspective neutral, because it encodes and links all possible choices of QRFs and their perspectives. And in fact, these maps are invertible on the physical Hilbert space, on the perspective neutral Hilbert space, and so you can concatenate them and also transform from one perspective to the other. Now, this, I'm using the word encodes on purpose, because this is actually what corresponds to the logical data in quantum error corrections. And in fact, we can finish the structural correspondence by relating one-to-one the logical information, which was the information we were interested in implementing in the quantum code, with the reduced Hilbert space in the QRF perspectives. And the inverse reduction map is going to provide an encoding, and since I said it's invertible, also its inverse is going to be a decoding. So there is really a mapping of the ingredients from one side to the other. But so far, I told you what the reference frame is from the gauge theory side, but I haven't told you what that is from the quantum error correction side. And this is the last piece of the puzzle, because it turns out that it is related to the choice of errors that you can correct for. And in fact, we prove at the following theorem that given a quantum code and a maximal set of correctable errors, this is going to be one-to-one correspondence with a choice of quantum reference frames. The way you prove it is that you consider the code space restrictions of your errors, and then you prove that they generate a subalgebra that, together with its commutant, give rise to a tensor factorization of your total Hilbert space into a frame degrees of freedom and the remaining degrees of freedom. And in such a factorization, you have that since this factorization is generated by the errors themselves, this means that in such a factorization, the errors are going to act locally only on the frame degrees of freedom. And so it turns out that then the correctability condition for the errors is essentially amounting to the fact that there exists a factorization such that the errors and the gauge transformation are only acting on the redundant degrees of freedom. So as you can expect, since they only affect the redundant information, then they can be corrected. So the logical information is protected against those errors. And this gives the QRF interpretation of the Kneel-Laflamme condition. So this is just to summarize. I haven't expanded on all the details, but to give you a flavor that there is a one-to-one mapping between all the spaces and maps in quantum error corrections with those in constrained quantizations. And you can find more details in the paper also about what type of errors can be described in a novel way compared to quantum error corrections from the gauge theory side. And then, of course, I said the next step is going to be to consider more general groups. And this is going to be useful because, in principle, quantum error correction is mainly based on finite groups and non-continuous groups. But the perspective neutral framework is well developed for generic unimodularly groups. So this can give new insight on how to design new codes and also have application in quantum simulation of gauge theories. And more broadly, we would like to understand, on the other hand, what you can say about gauge theories from a quantum error correction side. So whether you can understand the gauge invariant distribution of information in space-time as a quantum error correcting code. So that's all, and I thank you all for your attention. This is actually the full discussion.
Do you have questions?
There is one.
So there's been quite some work also on quantum error correcting codes and black holes in quantum superposition paradox. I'm very interested since you have this dictionary. Have you tried applying?
Could just.
Have you tried applying the dictionary to see what you get with error correcting codes?
We haven't, so I guess you're referring to the Hayden-Preskin protocol and works like that. You know, we haven't, but I mean, as I said, this is now for finite systems, so not yet for field theories, but of course we want to go to gauge theories and ultimately to gravity. And of course, yeah, that application is going to be, it's in our mind on the long run, but we haven't yet applied it to it. But I mean, there in principle, I guess an important aspect is going to be that you want to look only at the exterior regions. So that's a finite regions, and then it's tricky how you describe the gauge invariant degrees of freedom there. You will need to do some dressing, and there is where the reference frames are going to play a role.
The last part I didn't hear.
You use the reference frames to generate gauge invariant observables, so you will need to find suitable ways of declaring what's your reference frames in the context.
Let's thank the speaker again.
Thank you.
And our next speaker is Suleymanov from the Technical University of Vienna. And
I think it should be fine.
3 lessons in temporal quantum reference frames: causality, utility, and periodicity.
Working? Yes. Can everybody hear me okay? Yes? Thank you. So yes, thank you very much to the organizers, and thank you very much to you for managing to make it to a session that is running on currently now, I believe, past 6 p.m. So I very much appreciate that. So yes, my title is 3 Lessons in Temporal Quantum Reference Frames, but I foolishly realized that I'd forgotten my collaborator Ismail was actually already presenting the unitarity part, so 3 lessons became 2 lessons, and then I discovered that I only have 15 minutes to talk, so 2 lessons became 1 lesson. So if you came for the periodicity part, then you can come talk to me afterwards, or indeed to Fabio, who just spoke, who was also involved in that project. And of course, the unitarity part, Ismail knows better than I do. Okay, so causality. First, a quick note on terminology. So I'm going to use the words temporal reference frame and relational dynamics interchangeably because they are interchangeable. I will also, in this talk, use them interchangeably with the phrase, with the words Page-Wouters or Page-Wouters formalism. They aren't necessarily always interchangeable, and for some messy details, you can again ask me afterwards or see this paper at the bottom where we discuss equivalences between different formalisms of relational dynamics. So the talk will be divided into 2 parts. The first part will be a discussion of relational dynamics when multiple parties are concerned. And then the second part will be a discussion of how to try to embed the picture of operational causality within relational a framework of relational dynamics. And in particular, the second part will be concerned with this question: do causal relations change under a change of quantum reference frame? And if so, how? Why might we want to ask this question? Well, first of all, a space-time is up to a conformal symmetry, up to a conformal transformation, excuse me, equivalent to a set of causal relations on the one hand, and on the other hand, there is the so-called quantum equivalence principle that's being considered a lot recently as a way to try to understand space-times in superposition, therefore causal orders in superposition, by adopting the perspective of a particle in superposition, which itself seems to be subject to a single fixed geometry. So, as a spoiler, I'm not going to be able to answer this question, but I hope I'll be able to present you some progress towards it at least, and I'll be very interested to hear your opinions. So, part 1, relational dynamics with multiple parties. As has already been discussed by multiple speakers in a far better manner than I can do, in this approach to quantum reference frames, we begin with some kind of kinematical Hilbert space, where we have putatively some parties, and then on top of that we impose some kind of symmetry. Now this might be a gauge symmetry in electromagnetism, or might be the set of diffeomorphisms in general relativity, and the imposition of this symmetry means that there are of course a set of transformations under which our states must be symmetric, which in turn implies there are some generators of this symmetry. And so the set of states, can you see my cursor? Yeah, good. So the set of, actually, of course, I have this thing, that's what that's there for. Good, yes. So the set of states which are symmetric under those transformations are indeed the ones that vanish under the action of the operators that generate those states. So this may be familiar from the Page-Wouters context as the Hamiltonian constraint. It should represent the temporal reparameterization invariance of the theory in that case. Also known as the Wheeler-DeWitt equation in the context of canonical quantum gravity. And so, as other speakers have emphasized, while we may construct this constraint operator using the kinematical Hilbert space and the structures and the subsystem structure in particular thereon, it is not equal to the kinematical Hilbert space, and it has very different features, which I'm going to try to emphasize again and again over a series of slides. So, just as a quick example, again, you've seen this before, but it's good to go through it. We think about something bipartite and no interactions for simplicity. Our kinematical Hilbert space can be separated into a clock and a system. And then we have our Hamiltonian constraint just as a sum of the Hamiltonians of those two systems. And then let's allow ourselves an ideal clock for simplicity. So we have some time operator with some set of states with a Shelfer joint. We can relax this assumption, but throughout this talk, I'm going to stick to it. Am I too loud? The echo is very loud, though. I don't know if that means it's loud for you. Okay, good. How do we get dynamics relative to this clock? Well, as hopefully you know by this point, given the previous talks, we define this state relative to the clock via this reduction map, via the application of these clock time states onto the physical Hilbert space. So we arrive at this relationally evolving state in some Hilbert space of the system relative to the clock, which in fact is isomorphic to the original physical Hilbert space. And then this reduced state of the system relative to the clock evolves, or appears to evolve, with respect to the clock time in the usual manner as given by the Schrödinger equation. And we can write this in this kind of history state formalism, where this R here is a non-trivial assumption, in fact. And so one can see that this thing is encoding all of the information, and then this thing is kind of coming along for the ride. So what do I mean when I say coming along for the ride? I mean redundancy, as Fabio very nicely pointed out in his previous talk. There he is. Fabio nicely pointed out in his previous talk. So let's, for now, just relabel these, because we don't want to privilege one as being the clock and the other as being the system. Let's just call them A and B, right? So we have our constraint as before. These things are there to represent an ambiguity as to whether it should be an integral or a sum. So if we take some state from the kinematical space, we think this is bipartite, right? So we can parameterize this in terms of the energies of A and the energy of A and energy of B. And our state is completely defined by those two things. But if we're going to impose this constraint, then we have this delta function here. And we can choose to resolve that delta function in one of two ways, right? We can say, okay, I'm going to use the energies of A to parameterize my system. And then B is kind of coming along for the ride, and we have the wave function looking like this, and which we can then define as the wave function of A relative to B. And then again, this B system is coming along for the ride. Or we can choose to resolve this delta function. Where is it? There it is. We can choose, I think I'm going to use this because then I can actually see what I'm pointing at. Or we can choose to resolve this delta function in terms of using the B eigenvalues to parameterize. So then we can define this wave function of B relative to A in this manner. And so how does this relate to these Page-Wooter's reduced system states that are seeming to evolve with respect to this clock? Well, this part that's coming along for the ride, by which I really mean redundant, the choice of the degree of freedom which we've made redundant, if I hit this thing with the T on that this reduction map, this time state, that will hit this and just simply give me a phase here. So I can interpret this part here, rubbing this out, as the state at time t equals 0 with respect to B, or rubbing this part out, I can understand this as the state at time t equals 0 with respect to A. So we can use this picture to make a map of frame changes, right? We can this I showed you at the kind of perspective neutral level, if you like, at the level of the physical Hilbert space. But if we're talking now after the something's gone strange here. If we're talking now after the application of the reduction maps, because there's an equivalence between this physical space and the space after we get rid of one of the degrees of freedom and call it redundant, we can invert that and then apply the other map, and then the sum or the composition of these two maps allows me to move from the perspective with respect to A to the perspective with respect to B. Okay, so far so good. However, more parties, more problems. What happens now when we consider a tripartite space? I'm neglecting the tensor factors of identity now because otherwise it'll get kind of complicated. If we now have this non-interacting constraint and we impose the constraint, then we can write our physical state in the same manner as before, but now let's assume that this physical state is separable from C's perspective. That is to say, this wave function, so, okay, what do I mean by C's perspective? I mean I'm parameterizing the state in terms of the A variables and the B variables. And if I now assume that this wave function from C's perspective factorizes across the A-B divide, then I have a wave function of A relative to C, and I have a wave function of B relative to C. And then the C is redundant, coming along for the ride. Now, when I try to rewrite this, say, from the B's perspective, that is to say, using the A and the C variables instead to parameterize it, you find that I don't have something separable in this manner. I don't have a wave function of A relative to B multiplying a wave function of C relative to B. So under the assumption that there was separability from C's perspective, I arrive at the conclusion that it's necessarily entangled from B's perspective. This is what's sometimes called the relativity of entanglement, or the frame dependence of entanglement under quantum reference frame transformations. And you see it follows necessarily. There is no example of a state which is separable from both perspectives. And so one might like to see this as a transformation of the states, but actually that's slightly misleading. It's really about a transformation of what we mean by a subsystem. It's a differing tensor factorization. The physical Hilbert space, in this case, is separable or factorizes into an A part and a B part when you look at it from C's perspective, and it factorizes into an A part and a C part when you look at it from B's perspective. But the A part from C's perspective is not equal to the A part from B's perspective. So when we perform this transformation, we're not actually talking about the same system in a sense. This is what we call the relativity of subsystems and discussed at length in this paper. And in fact, as an aside, it may be that the factorization itself is frame dependent. So you can have a case where you're factorizable from C's perspective, but then when you adopt B's perspective, you can't talk about A and C separately. You have to talk about them as one combined lump, an AC system. Okay, so onto the causality part. So this is joint work with Veronica Baumann, who unfortunately couldn't make it, and I hope that it will be on the archive soon. Anything you like about it is credit to Veronica, and anything you don't like about it, you can count me for. So what do we mean by operational causality? We mean this kind of notion which classically is associated with people like Judea Pearl, where you have some kind of intervention on one party over here, and you're going to perform some observation over here. And if the observation you make over here depends upon the intervention you made over here, then you would say this thing causally influences that thing, right? And so when you want to formulate this in quantum language, as has been done by these authors, amongst others, we formulate this as some kind of transformation. I perform some intervention, the input here, and I perform some kind of observation of this output. And if this observation depends in any way upon this intervention, then this map somehow causally links A with B. So we come back to this question. Do causal relations change under a change of reference frame? And if so, how? That was the question, right? Now, if we think back to this slide, 4 slides ago or so, and then think about this diagram and say, okay, if we're going to describe this from a clock's perspective, then maybe you can already guess what's going to happen here. We have a problem immediately. As soon as you try to transform this intervention, it will become an intervention that, if it was localized, system localized, from clock 1's perspective, it becomes fully delocalized from clock 2's perspective. Likewise, what was a local observation on the party B becomes fully delocalized from the other clock's perspective. Now, this is an illustration of the fact that this factorization, A, B, C2, sorry, is a distinct factorization of the physical Hilbert space from the factorization A, B, C1. So we lose this locality, right? So this question is kind of out. What question can we ask instead? Well, how do we make interventions system local across different reference frames? How do we recover a notion of system locality that's robust to changes in reference frame? And the answer, which may surprise you, although it's only a partial answer, is actually you can make them system local by making them time local in a sense. So what we did there was to say, okay, let's allow ourselves these interventions and these observations, and let's look at how they transform under reference frames. But that's not really the lesson of the Page-Wootters formalism. Page-Wootters formalism kind of says you have a frozen universe, and everything should somehow be incorporated in that universe. And so if you're allowing yourself to be external and to make an intervention on that, somehow you're not really in keeping with the spirit. You're breaking somehow what the point of the thing is supposed to be. And so, how do we make things then time local? What do I mean by that? I mean by trying to condition them on the clocks, trying to say, rather than saying I will do this intervention maybe or not at this time, I say that this is the clock that's tracking the evolution of the system, and according to that clock, when it reaches a certain value, I want it to trigger something which will then perform the intervention. And this was, the formalism for this was laid out in this paper here by Esteban and collaborators. And so, what happens now, if you allow yourself or if you construct a model where your interventions are made in a clock-dependent manner, triggered by the value of the clock, you can indeed recover subsystem locality in a sense, right? You have a consistent picture of the intervention across different times now. You can see on the left side we have this clock 1 is triggering the intervention, and you're describing everything from clock 1's perspective, so it's simply happening in a nicely time-localized way. Now when you transform to clock 2's perspective, you broadly speaking have the same thing. So your intervention is still system localized, but now unfortunately it's become timely localized. You can't really perfectly localize it across different frames. So, in summary, the notion of subsystem is relative to the reference frame. The operational picture of causality as it stands only holds in one frame. It breaks apart under any reference frame any quantum reference frame transformation, in fact. But in Page-Wootters formalism, by explicitly timing this, you can keep the intervention system local at the cost that it becomes temporarily a little bit delocalized in another frame at best. Some open questions. Have we really solved the problem? Now we have two things interacting with a common system at two different times. If I say that the intervention affects the outcome, I mean, I've kind of given them a common cause now, so I can't, should I really understand that as a causal relationship between the two? I don't know. And the other thing is all of this assumed infinite energy, effectively, in the form of ideal clocks. And so if we actually allow ourselves if we restrict ourselves to the physical case, does this also make us, force us to a further time delocalization, or does it actually completely destroy the scheme? This is still an open question. So thanks again, Veronica. Thanks for the money, guys. And like my group, here they are.
If you can go 2 slides back. One more. One more. Operation picture of the Zelensky calls only 1 frame. Can you do the converse? Can you do the converse? Can you
define a frame by its
make indefinite causality into definite by performing a frame change?
That's an excellent question. I don't know. Yeah, I don't know.
Okay, let's thank again our speaker. So our next speaker is Yazdi from Dublin Institute for Advanced Studies in Ireland, and she's going to talk about statistical fluctuations in the causal set continuum correspondence. So.
Thank you, and thank you to the organizers of the conference. So I'm going to talk about some aspects of the causal set theory approach to quantum gravity, which have led to insights and phenomenology in both quantum field theory and cosmology. I'm going to talk about these things in very broad terms, but I will have a bunch of references on many of my slides that you can refer to for more details on what I'll talk about. Also, please come talk to me and ask me questions at any point after the talk. So in causal set theory, the fundamental underlying structure of space-time is proposed to be a causal set. A causal set is a discrete structure, or a partially ordered set, where the set is the set of space-time elements, and the ordering relation is the causal relations between those elements. So which elements are in the past or future of which other elements. Here's an example of a small causal set. So the circles or the dots are the elements of the causal set, and the lines are the causal relations between the elements, with the arrow indicating the direction of the relation. So for example, element Y is to the causal past of element Z, element X is to the causal future of element Z. Here's another example of a causal set, a bit bigger one. In this example, only the elements of the causal set are being shown, not the causal relations between the elements. And the elements are being represented as an embedding in a portion of 1 + 1 dimensional de Sitter space-time, which is what this particular causal set is approximated by. So the discreteness is expected to be around the Planck scale, because that's the scale of quantum gravity. And the discreteness is also fundamental, meaning that it's there to stay. It's not like a regulator or something which is going to be sent to 0 at the end of some calculation. We know that this causal set can give us all the essential information in a space-time. For example, the causal structure information and volume information or scale factor information that's usually provided by the metric. And we know this partly thanks to some powerful theorems from the 60s and 70s, some of which I've listed here, by people like Hawking, Zeeman, and Mele. So we know that the causal set can give us all the information all the essential information that we want from a space-time. And in addition, the discreteness of the causal sets naturally cures UV divergences, and causal sets are also frame-independent or locally Lorentz invariant. But because these causal sets are so different from continuum spacetimes that we're used to, an active area of research is to recognize and understand how some continuum quantities that we're more familiar with emerge from quantities that are more natural or more intrinsic to causal sets in the classical and semi-classical regime. Now, many quantities which are natural or intrinsic to causal sets are combinatorial in nature. So we're counting things, usually relations of some kind. And whenever we have a causal set function which has an analog in the continuum, the correspondence between that causal set function and its analog in the continuum tends to be statistical in nature. So for example, we have an ensemble of causal sets, C1, C2, etc. And we have some causal set function f, which maps from each of these causal sets to the real or complex numbers. And then it's averaged over this ensemble of causal sets macroscopically, and in the limit of the discreteness scale going to 0, would be approximated by the continuum function, which it is said to be approximated by or correspond to macroscopically. And these kinds of statistical average calculations that compare causal set functions with continuum counterpart functions can often be done either numerically or analytically. So here's an example of a causal set function which has a continuum analog. This B function or B operator in the causal set is the analog of the D'Alembert or box operator. So if we want to know the value of box phi at the point or element x, this is given by this B phi of x function, which is a summation over values phi with argument y, which is to the causal past of the element x, and then depending on how many elements I are in the causal interval between x and y, there will be a different weight or different coefficient in the sum. And the value of the coefficient also depends on the dimension of the space-time or causal set. So, so again, it's just a summation with different weights of values of the function phi with arguments to the past of the element x with different coefficients. And so this kind of operator, when averaged over an ensemble of causal sets, and in the limit of the discreteness scale going to 0, is approximated by the usual D'Alembert box operator, plus actually an additional term that's proportional to the Ricci scalar curvature. And this has been used to define the analog of the Einstein-Hilbert action in the following way. So the analog of the Einstein-Hilbert action in the causal set would just be this B operator applied to a constant function, which would kill this box term and leave us with the scalar curvature term, and then it's just a summation over all elements of the causal set in analogy to the usual integral that we have in the continuum. Now, we like to do these kinds of studies to check the agreements between causal set functions that have continuum analogs and their analogous continuum functions. But there are also deviations between these causal set functions and their continuum analogs. These deviations are both because of statistical fluctuations and because of finite discreteness scale effects. And these deviations are perhaps an even more interesting aspect of these comparison studies because they can be a very rich source of phenomenology. In this recent paper, we developed tools and techniques that streamline these kinds of calculations to study both the agreement between and deviations or differences between the causal set functions and their continuum analogs. I'm not gonna get into the details of how these kinds of calculations are done. I'm just going to give you an idea of some work that has stemmed from these kinds of studies. But for those interested, I'll just mention that these kinds of statistical calculations almost always can be boiled down to doing integrals over 3 kinds of domains, that over all the points in a manifold, or all points to the past of a point, or all points in the intersection of the past of 2 points. Okay, so there's a lot of interesting work that has been done in the context of quantum fields on causal sets. Some topics in this context include the choice of vacuum states. There is a proposal for a physical choice of state called the Sorkin-Johnston vacuum. There are interesting discreteness effects. So quantum field correlation functions are all naturally UV finite everywhere, and there are some short distance modifications to some known or familiar expressions from the continuum. We can study a space-time formulation of entanglement entropy, where this entropy is counted by covariant degrees of freedom, and this is especially important for the study of the microscopic origin of horizon entropy. We can also do Lorentzian spectral geometry because there is geometric information, for example, information about dimension, curvature, and other properties in the eigenvalues or spectra of causal set operators, such as the B operator that I showed you earlier. And these kinds of studies are also, from a practical perspective, numerically convenient to do using causal sets. So this is a list of references and work related to this. I'll just pause for a few seconds for you to skim some of the titles. No, almost. Okay, so there's also a class of non-local quantum field theories that have been constructed, and there's interesting phenomenology associated with them. So there are effects associated to the non-locality scale. For example, there are violations of Huygens principle and a proposal for a dark matter candidate which has come out of these theories. For example, well, maybe I'll skip the example because of so the value of lambda is related to 1 over square root of the volume of the observable universe, and the volume of the observable universe is changing over time. So the value of dark energy would be changing over time. And this is just a simplistic depiction of the fluctuating and changing nature of dark energy as simulated from one of the phenomenological models that implement this idea. And here are some references on this topic, and I'll end here. Thanks.
How do you put scales when you have a causal set?
Sorry?
Scales, you need a scale distance to make a volume physical, and you need also the speed of light to connect space with time. It doesn't seem to be working. Did you hear? Should I repeat?
Yes. So the scale is you set the scale as being, I guess, the discreteness scale. Kinematically, it's just put in by hand. Each element is assumed to occupy roughly a Planck volume. But perhaps when the full dynamics is developed, that scale should come out of the dynamics. But kinematically, we put in the scale by hand.
So you do have a cutoff.
Sorry?
You do have a cutoff, because the scale will be how spread are the points. No? So you have
the density of the points.
So it's not a regular cutoff, but you have a cutoff.
So the scale is what fundamental volume you would associate to each element of the causal set, which we take to be around the Planck volume, but you could set it to be 10 times the Planck volume, 100 times. Yeah.
Okay, let's thank again our speaker. Just a quick thing. Gaetano sent another email telling that the musical event that we are going to have now is going to happen in this room or in the other room. So, yeah, it's this one, so just stay where you are if you want to see music. And if you didn't sign the list of cost